7, 8. And how should I do this? Perfect. Alright. Thanks.
Does anyone in the audience have an adapter from USB-C to HDMI cable? Good morning, everyone. Welcome to the last day of the Granada Seminar. It's my great pleasure today to introduce Fernando Rosas. Probably you already know his work. His name already appeared a few times, several times during this conference. Fernando, he's a real Renaissance man. He has a background in every possible discipline that you can imagine. He's a musician, philosopher, mathematician, electrical engineer. So without further ado, Fernando, the stage is yours.
Thank you. Thanks a lot for the invitation and this wonderful workshop. And yeah, I'm here today to speak about my favorite subject, that is emergence. And I guess you have some intuitions already of what emergence is, but let me indulge you with some videos. So I don't know if you have seen this from some starlings flocking. So whenever we see this, just intuitively we have the feeling that there is something special happening, right? And the interest here is to try to put our finger on what exactly is happening and why is it special, and how can we measure this in interesting dimensions. And one thing that happens sometimes is that people say, yeah, emergence is a way of describing it. So it's all in the eye of the beholder. And I really think that, I mean, that's partially true, but I think the story is a bit more complicated. And about that, I really like this video about these little animals that are there, facing this opponent, and they would not be able to do that on their own, right? So here, this is a very concrete, clear example where the whole is more than the sum of the parts. And this is not a way of speaking, this is not a way of describing. Just because these little creatures are working together in such a unified way, they become this larger agent that has colossal powers over their world that they would not have on their own. So what is going on here, and how can we make sense of this type of phenomenon? Overall, so the big picture here that I represent is a pluralistic approach to the question. So not trying to say emergence is the single thing that I just have to find a single formula, but more of a multi-dimensional approach. So the idea would be to build frameworks to explain how wholes can have distinct properties. And I will divide this in different questions. One is, when the system processes more information than the parts, then how do new macroscopic regularities arise from the dynamics of the microscopic? And third, what is this good for? What can we do with this? And as I said, the proposal I represent in this talk is to say that emergence is not this single thing, but has multiple facets and I will discuss two in particular. One is something we call sometimes mereological emergence. That means specifically about wholes and parts. So when whole has distinct properties on their parts. And then another approach that I will describe as computational closure, that is when there are distinct regularities happening at the macroscopic level. And so that's the plan for the talk. And for doing this, then the first section will explain the first approach to the question. The second approach, the computational closure, will be in the second part. Then I will show a little bit of an application that I have been working following this line, so in the realm of AI safety. And then I will conclude with some summarizing ideas. So the first part of the talk, this is work of Pedro and some other wonderful collaborators. And here the question would be, when do systems process more information than nucleus? So to start grounding these ideas, I will informally define emergence first in this first approach as when the whole exhibit properties that cannot be traced down to the parts. And one way of thinking about it is that we have dynamical systems made of parts, so multivariate stochastic processes. And when we think about them in the standard way, we tend to think with these arrows. I mean, it's like when they have transfer, or when they have synchrony, when they have memory, there's something that stays in the same place. But we have been hearing these last days about high order things. So where is the high order here, and what is that doing? What is the high order dynamics? And for that, we came with this framework, where the framework is the following. We have a multivariate system, X, time t, and this is a vector, so each of them has their own dynamics. And we're going to define a supervenient feature as a compression of the microscopic description of the system into some simpler thing. So imagine, for example, each of the x1 to n could be the position of a bird in a flock, and the v could be the center of mass of the flock. So it's a simpler description of the whole thing. And because the micro has their own dynamics, that induces some dynamics in the macro. So v will also be a time series or a stochastic process. And the interest is to understand how the dynamics of the micro relate with the dynamics of the macro. And we will define, this is just out of the pocket definition, we will say V is causally emergent if there is some formula. And the formula is saying V has unique information about the future of the system with respect to the parts of the system at the same time. All of this will be defined in terms of partial information composition, but because we are experts already with all the talks you have seen, I will not get into the nitty-gritty, but I will explain a bit how to measure it. Now, intuitively, at this point you could complain, very rightfully, say, how could it be that E, that is a compression of X, have unique information about anything? Because any information that is in D has to be already in X. So what is going on? And here the trick is the conditioning part of this equation. So the conditioning is not with respect to the vector as a whole. Because if you consider everything that is in X, then there's nothing that is in D that is not in X. But if now you consider the parts in isolation, you see one of them at the time, that there could be something in V that is not in any of the parts. Something like a bivariate information or triple information or high order information. So that's sort of the intuition behind this equation. To get a more concrete flavor of what type of emergence this refers to, this is a toy model. It is a very artificial one, but very clear. It's sort of a minimal example of this phenomenon. So here, this is a stochastic process. We have binary time series. We initialize them at time 0 randomly, so you flip 2 points. And then the rule says, whatever the parity is, so if they are equal, they are going to tend to keep being equal over time. So in this case, we start with flipping the coins, we get 2 whites, and because they are equal, with high probability, they stay being equal. However, they can be equally white or equally black, that is completely wrong. So they're going to stay being equal for very long, and at some point, by a low probability, they're going to flip to start being different. And then they keep being different consistently, until at some point they flip to be equal again. So this is the statistics. You can define this mathematically, you can run simulations, you can sample this process, you can do whatever you want. What is very interesting is that if you are one of these two processes, let's say I'm x1 at time 0, and I know I am white, what can I tell about the world? And the answer is absolutely nothing. Like nothing that any of your states is completely irrelevant to what will happen in the future because of the definition. The only thing that propagates is, are they equal or are they not equal? But the fact that it's white or black, any of them, doesn't matter. So if you're a citizen in this world, would think that your efforts make no difference, because whatever your state is, nothing will change. However, and then at that point, as an individual, you will think there's nothing going on. This is just a random world. But this is not a random process. As a whole, there is information being propagated between past and future. So the parity has causal power on what's going to happen in the future. But that parity is not localized in any of the parts. So this is the type of emergence that I'm capturing here. So we have these two subcomponents. Each of them has no idea what will happen, but there is a collective property of them, in this case, are they equal or are they not equal, that has causal power. So the parity will be the B, and V will be causally emergent in this domain. Does this make sense? So this is the intuition. This is a super simple example. Now let's first get some theoretical results. So far it's just a definition that me and Pedro and other people came with. But what are the consequences mathematically? The first consequence, you could ask, okay, here I have a stochastic process and I have to be smart enough to find what is the right property. Is there any property in the dynamics of the micro that says there is something emergent? Is there an intrinsic characteristic of emergence at the micro level? And the answer is yes, and that property is synergy. So one can prove that the system at the micro level has synergy if and only if there exists some coarse graining that has this property. And this is a very information theoretic-like result. It will not tell you which is the coarse graining, it will just tell you it exists. So synergy is sort of the intrinsic flavor of emergence in this perspective. And the synergy that I'm talking here is you take each of the components in the IT as a predictor and the joint state of them in the future as a target with prediction. And then you're asking yourself, can I predict more because I know all of them at the same time versus knowing each of them separately? And the answer is you can predict more. There is some coarse graining that has this property. And this is a very satisfying theoretical result, but it's not very helpful for applications, because if you want to measure this in real systems with hundreds of parts, we're getting very complicated to measure this. So what makes this theory very powerful empirically is that there is this second result that says there is this criterion, this is a simpler formula, is simpler than synergy, that gives you a sufficient although necessary condition for emergence. So here, the first condition is about the intrinsic properties of the system to have some emergent property. This is testing a specific candidate. So here you have your favorite candidate, B, this function that I really like and I really hope is emergent, but I don't know, so I want to test it. You compute this quantity, and then to get an intuition of what this quantity is, the first component is the mutual information of the candidate feature between two entire points. So it's some type of nonlinear autocorrelation, how much you can predict yourself. And then you ask how much I can predict the future of this thing from each of the components. So imagine we would be measuring a flock of birds, so V could be the center of mass, and then you ask between two time points the position of the center of mass, how much it tells you where will be the center of mass in the future. So how much the center of mass predicts itself. And the second part is how much each of the birds at time t can predict where the flock is going to be at time t. And then you sum those predictive powers, and you say if all the birds, if the predictive power of each of the birds, you add it up together, and doesn't explain away the self-predictive power of the flock, that means that the flock is emergent. And lo and behold, we measure this. Madalena showed this a little bit yesterday, but I will show it again with some animations. So here we have the Raynaud flocking model. This is one synthetic, artificial, very simplified model of flocking. But then I think it has parameters, so you can play with these parameters. And we play here with this avoidance parameter that in one extreme gives you these very rigid birds, like militaries, marching around each other. In the other extreme, they're completely crazy birds, they don't care about anything, so there's a disappointing flock. And in the middle, you have some mix. And the intuition here would be, well, we measure this quantity, and this is what happens. So in the two extremes, there is no emergence, and in the middle, there is emergence. But the interesting thing is that in the two extremes, you have no emergence for different reasons. In the military bird example, everyone predicts where the flock is going, because the thing is so rigid that every bird knows where the thing is going, so there's no emergence. In the crazy bird example, nobody knows where the thing is going, but the flock also doesn't know where it's going. So again, no emergence. But in the middle, there is this sweet spot where the birds don't really know where the flock is going, but the flock knows where it's going. Because of the averaging, there is some self-consistency in the dynamics, which make the flock to know where it's going, but every bird that composes the flock don't know where it's going. So this is the type of emergence that this tool is designed to capture. We have a number of applications of this metric that I will not explain, but I will just briefly highlight. So this is one that Pedro showed the other day, where we measure the capacity for emergence, so the synergy of patients with vegetative condition versus controls, and the worse your brain dynamics condition is, the less capacity for emergence your brain dynamics have. So there seems to be a correlation here between healthy brain dynamics and the capacity for those dynamics to have emergent properties. Then there is an upcoming paper, so there is this very old question about brain oscillations. Are they a phenomenon, or are they like if all the neurons are firing, is more likely that this other neuron will fire also, things like that. And with this proof, we can measure this, and we are finding very interesting results that in some situations, depending on if wake or sleep conditions, the time scale where the emergence happening is different, and all sort of things. This is an upcoming paper, it's not published yet. There is another paper from the group of Pedro here that they study recurrent neural networks, and they would train them to predict different chaotic systems, and they found that as they train these RNNs to better prediction tasks, better prediction performance, they get emergence as the side product of the input at prediction. And also they train the opposite, and they train for emergence, and then the reservoir started the input at prediction. So there seems to be also a correspondence between, in some situations, between emergent dynamics and the prediction. And finally, the results that Madalena showed yesterday, where we have this human experiments where they move dynamically, and we have all type of interesting correlations between the emergent properties of the whole and the aesthetic experience of people seeing this pattern, and how connected they feel with each other, etc. So if you're interested in any of these applications, let me know and I can send you this paper so you can see a bit more. At this point, I just want to say this is very practical and can be used in different contexts, and allows to find nice insights and complex systems. So, as a summary of this part, synergy quantifies information that arises from interaction among parts beyond what contribute the parts. So synergy is a way to measure when the system as a whole is computing more than the parts. And emergent in this scenario is understood as a synergistic dynamics where there is some collective property that can predict better the future than the parts in isolation. And empirically, we have seen that this type of emergence is associated with different things like healthy brain dynamics, effective group coordination, good performance in performance networks. So this is one way of measuring emergence, and in the beginning when we start thinking about this, I was like, this is emergence, this way of measuring. But then there are other people measuring in different ways, and the more I start thinking about it, I start seeing benefit in all of this in different ways. So I will now present another way to study emergence, that you will see that it has some similarities, but it also has its own distinct flavor. So let's go now to a different type of emergence. So this is work done with some overlap with other people, but also different people, and sponsored by Eclipse. So the question that we're going to target now is, under what conditions there are new regularities emerging at the market level? And for this, we first start with some definitions and key ideas, and then explore some applications. So this came from thinking very hard about computers. So when the lockdown happened, I started using Twitter for the first time. It was a mistake, I guess. And in Twitter, every 6 months, people start fighting, is the brain a computer? No, it's not a computer, it's not a computer, and blah, blah. And usually, when we apply standard definitions of what a computer is, you don't learn too much about the brain, which I found would make the whole discussion really happy and interesting. But then we start thinking, can we rethink what a computer is in a way that is more useful for neuroscience? And thinking about a laptop like this one, a laptop is a physical system that whenever I write an algorithm like this one in the screen, I press enter, the thing starts computing, and start following the laws of physics, right? So it's the same as a ball in top of a hill falling down, following the laws of physics. So what is the difference between my laptop and this ball falling down the hill? And the claim here is that the laptop is different. There is a intrinsic difference between the ball and the laptop. And the difference is that whenever I can run my laptop multiple times, the same algorithm, and every time I run the laptop with this algorithm here, I will get a number 5 print from the screen, right? So the most some and you print, I get a number 5. And I do it 10 times, and I will get 10 times the number 5. However, the physics that are leading to that number 5 are going to be different every time I run it. They'll be completely different. If I focus on speed number 10 of my whatever, it will be up or down or it will do whatever. So there is a core training at which the dynamics are very controllable. And I can set my things, and I'm just setting like macroscopic initial conditions, right? I'm saying like I want this input, so I put some inputs into the algorithm, and the physics run, and they run in a different way every time, but the macroscopic output is the same. So there is a macroscopic level that is very controllable, that is very simple, and sort of self-contained in a way, that is supervening on microphysics that is a complete mess. And whenever you have, I don't think you can do that with the rock. There is no way to program the rock such that every time it goes, in an interesting way, because say every time it goes, you get the same algorithm, but you cannot reprogram it. So this is, in my view, the difference between a computer and a laptop, and the whole difference is that is this software, this level of description that is self-contained. Now, let me try to convince you that toilets have software. And the claim is the following. Every time you flush the toilet, the water will go out of it, right? And then the water will slowly come in, slowly, and there's this floating device that is down, and at some point the water will push out this floating device and it will close the water in. And then the thing stops. So in programming language, that is called a while loop, right? It says, while the water is down, keep putting in, and as soon as the condition is met, then close. So there is logic in the toilet, and that's why toilets are useful. And every time you run this logic, the hydrodynamics of the turbulence of the liquid is going to be a complete mess, but you don't care because the software is ignorant of those, Navier-Stokes equations. Although it's made of that. So it's the same thing as the laptop. It's made of physics, very complicated physics, but it has a level of description where you have this algorithm that runs very reliably. So in my view, software, toilet has software, and not only that, like everything has really software. So the idea here is that there's this logic in the macro where macro interventions are sufficient to determine macro effects, macro consequences. And if you think of a self-driving car, it's the same thing. The self-driving car has these little cameras and sensors, and it's moving around in a quantum world that is completely super complicated, and it has no idea about the quantum waves that are collapsing or anything, but it's driving, and sometimes successfully. And we do the same, right? We live in a quantum world, we have no idea what quantum states are around us, and we survive. We can choose our menu, we go to sleep sometimes, and so it's sort of the same thing happening always. Now, how can we measure this? Now that we get this vision, there's a software that we could recognize in many places where we don't actually think about software. One way to start thinking about this mathematically is with this notion we call information closure. So, and the idea of information closure is a bit similar than before. You have a microdynamic effect, so different time points, you have a close gradient that is set. It could be spatial or temporal, or it could be just time by time. And now we do the following game. We want to predict the future of set. What is the next screen that I will see in my computer? And you do the prediction either from the past information at the coarse grain level, that's the first term of information, or you do it with micro information. And because we are in Shannon world, here information never hurts, there's no fitting anything like that. Information is always good. So the right hand side is always going to be at least the same as the left, and usually larger. So you do better if you do more. But in some situations you will do as well. And that is information closure. Another way to think of it, let's say you have this information, macro information, and you want to predict the next macro step, and you could pay money for see how these macro states are made into micro states. And the question is, should you pay that money? Is that money going to pay off and give you a better prediction? If the answer is no, that means that all the relevant information was at the macro level in the first place. And that's information closure. So every relevant information, it's not that the micro information is irrelevant for predicting the micro. It might well be. But for predicting the macro, maybe just you need macro information. A good example of that is thermodynamics, right? So if you want to know the future volume of something, you don't need to ask what is the momentum of this particle. You start asking what's the temperature, the pressure. So it is the same. In thermodynamics, you have this course, a self-contained level of macroscopic descriptors that play with each other, irrespectively of how they are instantiated with the micro level. Good. So, to get a bit further with this intuition, we have this idea of computational mechanics. And let me introduce it. This is a framework built by Jim Crutchfield and his colleagues for many years about how to build a computational representation of dynamical processes. So, how this works. The first step is to build a HMM representation of a time series. So you have a time series, you have some data, let's say we have this microscopic data, the dynamics of the toilet, and you want to understand how this is working at the micro level. The way this works is that you say, okay, I have my stochastic process, maybe it's very complicated, non-Markovian, high memory, very complicated. So the first thing you do is that you span the phase space of your process. You say, let's say your process is binary, to make it simple, but it's very non-Markovian, very complicated. So the first trick you do in your mind is to say, actually the phase space is not binary, it's histories. So the actual phase space is history. And so you build history, and then you compare histories depending on the predictive power they have. So for each history of bits, in this case, you say, what is the likelihood of this happening in the future, or that happening in the future? But whenever you have two histories that have the same predictive ability, they give the same predictions for everything, you say, these are the same. So you merge histories that have the same predictive powers, and you separate things that have distinct predictive powers. If you do that, you get this very canonical latent model. So these equivalent classes of histories are going to be the real states of your process. And then every time you see the next measurement, you update the equivalent class where you're going. And that gives you what is in the right, this latent structure, this hidden market model, where the green states are these proper states of your process. And the blue states are the emissions, are the next states that are happening because of this. So if you're familiar with HMMs, that should be natural if you not a little bit. But the take-home message from here is that there's this standard way to build minimal latent structures that explain your data. Now, what is this? Why is this interesting? Is that, well, for a number of reasons. The first is that you can do this game at different levels. So if you have micro data, you can build this latent state for the micro, and you can do the same for the macro. And then you get this E prime that is the latent state of the macro, and you can ask yourself, how is this two things related? Another thing that you can do is to build a latent state of the micro about the future of the macro. So something that goes in diagonal. And here what you would do is that you consider histories of the microstates, and you group them if they give you the same predictions for the future macro. So imagine that this is setting an experiment, setting the initial conditions. So you set the initial conditions and you see what happens at the macro level. And you set the initial conditions in a different way, you see what happens at the macro level. And you only separate the initial conditions that give you different macro consequences. So that's sort of macro controllability, right? And one definition of causal closure would be when the controllability at the micro doesn't give you anything more than the controllability at the macro. So any initial condition that will give a different consequence, you could achieve it controlling it at the macro level, and you don't need to get these very thin fingers to set your states in a very particular way. You will not gain anything macro level-wise. So this is a separate definition. The first one is information closure, when the macro is sufficient to predict itself. This is causal closure. The macro is sufficient to setting the initial conditions that make a difference. And now the exciting part of this epsilon machine story is that there are HMMs, there are these latent dynamical systems that model the data, but they also can be interpreted as automata. And I don't know if you have heard of automata. These are not Setter automata in the complexity science way, but more automata in the computer science way, like Turing machines and stuff like that. So every time you have a time series, there is a canonical way to build this machine that has states. And now the data you observe is not emitted by the hidden state, but more like inputs that you put into the state, and that makes a transition to the next state. And every data you have, you put this inputs, and then you start having this walk around the states of the system. And now this allows you to see the computational process that is happening associated with this data. And I find this very beautiful because it gives you like a duality between dynamics on one hand when you see the structure of HMM versus a computational perspective when you see this other perspective. And you cannot do this generally. If you have a general HMM, you cannot transform it into an automata. But these are special HMMs that have some property called unifilarity. It's a technical property, but that is what allows you to do the transfer and see things in this way. And now with this you have this idea that there is this machine that is jumping between states, and this jumping between states is what's really generating the data you observe. And now what comes the interesting part in my opinion. So you have the data coarse grained at different levels. So let's say you have quantum data and then coarse grained, you have classical data, and you can build machines for each of your data. And these machines, I think of them as theories. It's like a theory that you propose that is explaining the data that you observe. And you can build machines at every level of description. So the natural question is how these machines are related. Are they related to each other? And naively, I thought, as you simplify yourself, machines should become simple, right? But that is not true. And in general, they could become arbitrarily more complicated. One thing that can happen very often is that if you have a microprocessors are memory-wise very simple. If you coarse grain a microprocessor in a random way, usually you lose macrounity. And you start having a complicated memory. And that is reflected usually in a bigger machine. So most coarse grainings are going to make your machines explode. And the good coarse grainings are the ones that simplify the machine. So, and what does it mean to simplify a machine? Here we have a machine with little states. Yellow states, and you have the inputs are the arrows that make the transition between the little states. And the one question one can ask is, can I group these small states into bigger states such that I get a bigger machine that is sort of a Russian doll that is inside of it or containing it? So you get a simplified machine that is tracking less details of what is going on. And this is a good effective theory. It's an effective theory that is only tracking the relevant aspects of your macro theory. It's not more complicated, it's actually more simple. And this is the good coarse grainings. So for this, we define computational closure as the coarse grainings of your data such that the resulting machine is simpler, and there is a commuting diagram in the sense that if I have my micro data, I compute the micro machine. There is a way to coarse grain my micro machine to a macro machine that is the same that I would get if I coarse grain my data and then I compute the machine. So it's like if you build a quantum theory, you can coarse grain your quantum theory to your classical theory. But it's the same as if you coarse grain your data from quantum data to classical data, then get the theory. So those, when you have that commuting diagram, then you have a happy coarse grain. And so those are the elements of the story. Now, what are the implications? The first is that there is information closure is equivalent to closure. These two first definitions that I said, the optimal prediction and optimal expression are the same, because we are assuming, and this is the caveat that these are and if there is no unobserved variables, that's true. And the second consequence is that information and concept closure implies population closure. So if you have this coarse graining that gives you all self-contained information and self-contained interventions, you can guarantee that you have self-contained computations in the way I described. And then this is sort of the master plan. So you have all the coarse grainings that you could do for your system, then you keep only the good ones that are causally close. And then for each of them you can build machines, and you also know that the machines are going to be coarse graining of each other. And this is going to give you a multi-scale description of the computations of the process. Let me illustrate this crazy idea with a concrete example. So here we have a network, a modular network, so strongly connected within communities and weakly connected between. And we have a random walk over this. So you have a drunken person, then starts in the right, and stays in the red, and then sometimes it jumps to the blue or stays in the red. So that's the process. The claim here is that, and the probabilities of transitions are proportional to the weights of the legs. What happens is, because of the symmetries in this problem, you can coarse grain your description and only track in which community the random walk is. You forget about in which node you are. Or you can further coarse grain and say, what is the size of my community? I don't care even about the identity, I just care about community size 25 and And each of these levels are informationally closed, causally closed, or computationally closed. So what are the implications of this? For example, you could run your process at the macro level, and you could do a simulation, and that simulation will be perfect. You are not losing any data because we're not simulating the levels. Or another thing you could do is that you are the running the water, and you know where you're standing. And your next decision could be made as a cascade of decisions. First, you could say, what is the size of my next community? Okay, you decide that. Then you say, okay, within the community this size, which is actually the next community I'm going. And then you decide that. And then you say, okay, within this community I'm going to this now. So you can factor these computations in all these levels. And that is what is allowed by this lattice of questions. Well, I'm running out of time, so we computed this for the airfast diffusion level. If you're familiar with classical dynamics, you have particles in two chambers that are randomly jumping between them, and you can prove that if you compute the number of particles in each container, that is computationally closed and informationally closed, which is consistent with the intuitive understanding that usually thermodynamic quantities are close and self-referential in distance. So this is happening in this. And in Hopfield networks, you can coarse grain. So let's say you have a Hopfield network with the activity of the neurons, and there are all these candidate patterns at which you could converge. You can compute the dot product of your present state against every candidate, and then you make a vector of the projections of your present state for all the candidates. And you can prove that this is also computationally closed. And that means that if you want to know where the thing is going, you don't need to track individual neurons. You just need to track these projections. And usually what happens if you plot these projections, one in the beginning they're all like messy, but one of them will start growing, and then you know that that's where things are. And if you flip neurons in a way that all these projections stay the same, nothing in the dynamics will change. That's completely wrong. But this is capturing all the aspects of the dynamics that really make a difference. And as an ongoing project here, we have been training transformers, small transformers, on data generated by these multi-scale processes. And it seems, based on preliminary results, as you start shrinking the capacity of your transformer, the number of dimensions in which you can code stuff, the transformer, if it's large enough, it will predict the process at every level. But as you start shrinking it will not be able to predict the microdynamics, but it will predict the macrodynamics. So it seems that when you have resource constraints, these transformers are naturally finding these computationally close limits, which makes sense because it's like, okay, I cannot predict this whole thing, but if I restrict myself to this abstraction, I can predict really well. So an interesting conjecture is that these are natural abstractions that resource constrained systems are naturally going to converge to. So the summary of this part, as you can see, this is a completely different flavor of emergence. There is no parts. There is a whole micro that is not differentiated into subcomponents, and it's all about when the macro self-contained itself is expected to be instantiated. So emergence as closure highlights scales that are computationally autonomous, and computationally closed levels can be efficiently controlled and can be run on their own without running below. So it has interesting properties for agents living in them because they can live at a, like for example us, we live in it seems a computationally closed level, so we can survive classically. And also as a simulation, if you're simulating a system, if you know all these levels, you can choose the level of simulation and avoid over-simulating things. And it seems that transformers naturally identify this. And I have this, but I have 3 minutes, so I will do a super quick highlight the description of what's going on here. So this is one application of this idea, and done with these people and funding from area. So the question here is somebody gives you a robot, and it's like, oh, I have this robot. So you don't know how it's built, but you know the type of actions that the robot can take and the type of sensory information that can come into it. So the idea is that you will build a simulator, it's like a matrix. You build a world model for the robot that for given actions it will generate stimuli. And the idea is that you will build it in a nice way so you can test the robot and see if it's dangerous or what it can do, what it can do, things like that. And let's say you have a model that is indistinguishable for the robot from the robot. Sometimes that's not the end of the story because maybe you're over simulating. Maybe, for example, your world model for your robot, you're simulating the whole galaxy at the quantum level, or maybe the robot is very crappy, it's a Roomba, and can only take your room or something. So maybe it's a good idea to shrink your world model to keep only the relevant scale and the relevant components. So maybe the agent is classical, you don't need to simulate quantum, it's only in a corner of the world. So the question here is how can you minimize worlds for agents? And the thought experiment, as I don't know if you're familiar with this, the brain the vat. So it's a thought experiment from here at mine, from philosophy of mind. You take a brain, you take it out of the skull into this glass, and you put some wires, you measure the actions from the motor cortex, you process them in a computer, and you generate signals that you feed it to the visual cortex and the auditory cortex. And if you do the simulation right, the thought experiment says the brain will not tell the difference between reality and this computer. So following at the same lines, they used to put the AI in a vat and run a simulation such that for the AI would be completely indistinguishable. And by doing that, there are two questions that are interesting. One is how can you simulate, how can you compress the world the most, which will tell you how intelligent is the agent. So if the agent is not very capable, you can simulate a very simple world and the agent will not know the difference. If the agent is very powerful, the world will be very large. And also, can you characterize by this minimal world what is learnable from the agent and what are the capabilities, basically? And long story short, we have answers for all of this. Okay, let me walk you a little bit on the basics. So the first step is to say, forget about the world. Think about the interface of the agent. So you focus on the action, you focus on the observations, and you focus on the probability. So given a sequence of actions, what is the probability for the agent to observe a sequence of observations? That's the interface. There is no world. There is just these conditional probabilities of observations given action. And this, in a graphical model perspective, looks like this. You have a big sequence conditioning another big sequence. And as you know, this is completely, you cannot simulate this in a computer. It doesn't scale. So worlds are these third variables that you can bring out of your pocket. You always imagine it, but they factorize this thing. This is the magic of growth. You have this massive graphical model that is completely uncomputable. But if you imagine a world, the world has this property that factorizes graphical models and then you can compute step by step. And the proposition in the paper we wrote is that these are worlds. Any third process, so that's the process that you imagine, that has this property that we factorize things in the right way, this is a world. And the consequence is that for any interface, there are many worlds. So we could say we are all humans, we all share the same interface. There are many worlds that we can imagine that are transducing our actions into our observations. And maybe you have different religions or different beliefs and whatever. Each of them are worlds that are factorizing the thing in a different way. And we can be agents with the same interface, but we can live in different worlds. And what's interesting, you can ask, for example, okay, I will skip this. So for any interface, you can always construct at least one world. And that world is the history. You will put everything that ever happened into a single variable as a world, it will factorize. So every interface has a world, but some of them are not very useful. So how can we compress worlds? How can you take a world like this that is exponentially growing and compress it? And there is a way to compress that is you take a function and you just compress the world, but you check if the function is keeping this property of factorizing things in the right way. And this is called in the literature bisimulation. You have ever encountered. And what you can do once you have the definition of bisimulation, you can define isomorphic worlds. You can have a world and you can bisimulate it into another thing, and then you can bisimulate back. These things are clear. It's just relabeling of the same state. You can then define a minimal world. A minimal world is a world that every time every time you bisimulate into something else, you can bisimulate back because it's like you reach already the bottom of this thing. And once you define this, you can ask, okay, let's say we take two humans, we take their world in which they believe, we start bisimulating. Are we going to get to the same point? Is there a single minimum world for a given interface? And the answer is no. And this was very striking for me. What happens if you start from different worlds for the same interface, you start bisimulating, you're going to get to different local minima. And that's it. So at this point, you have two options in your life. You can accept that reality is hard, and there are minimally uncomparable worlds with the same interface, or you can take a leap of faith and embrace negative probabilities. And so what is a negative probability? It's something that makes no sense. But what happens is that worlds are something that are minimizing something that when you restrict the condition that probability has to be non-negative, you get better outcomes. And it so happens that once you embrace HMMs with those worlds with negative transition probabilities, you happen to get a single minimum. So in my interpretation, this is the mathematical foundation of the idea of Kant, that things in themselves cannot be observed. So this minimal generator of an interface is usually a process that you cannot, it doesn't run stochastically, but it runs in a black box way. You can run the numbers and then it generates the observation with the right probability. This is a bit like Kantian in a way. So you have this minimal generator, it's a black box algorithm. It will generate the same word, the right word for the agent. But once you try to reason about it probabilistically, you can't, because you have this negative thing that makes sense. But it's unique, and that's good. So from the side, this is the answer of how you should simulate the world of an agent in an optimal way with these negative things. But then you have to forget about interpreting anything with what the agent is. And if you want to understand what it's thinking, we have. I will not explain the details, but I will just explain the conclusion. That is very interesting. It says that if you have two humans with the same interface, I already said that if you want to minimize, really minimize, you end up with this negative thing that makes no sense. But if you consider worlds that the agent could compute in real time in its head, then there is a single minimum. And this is very related with epsilon machines and these collapsing trajectories and the same thing. And so the bottom line is that agents can disagree on their beliefs when there are metaphysical stuff associated with them, but when it's only about stuff that is empirically verifiable, they cannot disagree. So there is another foundation here for science. That is like, okay, if we're going to talk about facts that we can do experiments and test, we will have to agree. And there is this minimal world that is the same for every agent with the same interface. Now, if we allow metaphysics that we cannot test, then we will disagree forever. And all of this can be proved mathematically. If you check the preprint, they have like infinite number of appendices with all the derivations. So to conclude, the class of world models that can simulate the same interface is surprisingly rich. I was very surprised that the answer is so diverse. There is this fundamental trade-off between computational efficiency, that if you go for efficiency, you get negative transitions that are completely weird, or interpretable worlds that are the ones that the agent can compute in real time. And then you have a single minimum that is the one that an optimal Bayesian super efficient agent will converge to. And by checking that world, you can interpret what the agent can learn and what it's thinking, etc. Yeah, in the last minutes, let me explain what I'm doing right now with all of this. So I'm studying, for example, a variation of the airphase model. So we have two chambers and the gas, etc. But now we have an agent that can do stuff. And the agent will be able to push particles between the chambers, and the agent will receive information about which is the good chamber. So they will say, oh, the good chamber is the first one, so we'll start pushing particles in one direction. And then the good chamber will change, and then it will start pushing particles in the other direction. So you can train a reinforcement learning agent to learn this with different number of particles. And what happens is, when you have 5 particles, the agent will learn. The blue is when the agent controls individual particles. So the agent with real particles will learn and will do great. But if you have 40 particles, there are 2 to the 40 states, so the agent will never learn. It's too hard. So then you can have a macroscopic agent. So you can use all the story of this abstraction, and then you say to the agent, forget about your detailed measurement, just take the mean, sum the particles that you observe, and forget about your detailed control information, just push some particle in one direction or the other. So with that, you have a linear number of states, you have 2 actions, and you have this orange curve. And you can see here that if the number of particles is very small, the microagent is better than the macroagent. But as the number of particles start growing, the macro outperforms to the point that there is a point where the microagent has no hope of learning anything, but the macroagent does pretty well. So what I'm working at the moment is to apply all these ideas to understand abstractions in reinforcement learning and see how you can simplify problems in ways that you will have a trade-off. So every time you simplify, you use information, but maybe you keep the relevant things for your reward, and then you can learn in things that are scalable instead of being crazy and like using the whole budget of the planet in order to learn this stuff. Right? So good. So to summarize, I'm sorry I'm a bit over time, but what is emergence? Have we learned that? Well, sort of. Not really, but the idea, my way of thinking is that emergence is a bit like intelligence or a bit like complexity. You tend to think that it is a thing, but the more you stare at it, you realize there's a bunch of things that are related. And it's useful to be able to switch between these two perspectives. It's one thing, but then when we really become serious to talk about it, it's actually multiple things that are similar but can be disentangled in their first level. And then, if we embrace that view, we need different formalisms to capture each of the faces, and we need to understand how these formalisms relate to each other. So here I presented two such formalisms. The first one is emergence as computational closure, and here the whole thing is about decoupling between macro, and self-containment and stuff like that. The other one, the first I presented, is about emergence as whole versus parts, and this is very different about how the collective relates to subcomponents and what the collective can do and the parts can do, stuff like that. So are they related? Of course they're related, but when you try to really connect them, it's very hard. And actually, I don't know exactly how these two things are related, if they are related. So one of the quests at the moment is to try to understand their connections, and also I'm pretty sure these are not the end of the story. There might be other facets that we need to add to this polygon to see the whole picture. Is the answer? We don't know, but all of this is very recent and it's very exciting, so I have to keep working on this. Thank you very much.
Thanks, Fernando. Yeah, we have time for a few questions.
Hi, thank you very much. I think I like everything that you have presented. So what I'm going to say is probably people are going to kill me afterwards. I'm going to make a comment about the central part of your talk, particularly. I will try to be able to make the point, but I don't know if I will succeed. And even if I succeed, people are going to kill me. So I think that those efforts about causal closure and those kinds of things, I think that they are misdirected, and I think that they are essential. I think that they are great. I use them in my PhD thesis, and I think they're cool. But I think that they are essentially a reductionist approach to do something that is essentially not possible to reduce. Particularly, I think that the causal closure, it comes short to reality. I mean, it allows us to aspire for macro causality, to be at most as good as micro. And I think that this is wrong. And I think that when you say your micro epsilon machine or whatever can predict as much as the macro, actually it's not you, but the process is cheating. Because the only reason why the micro is able to predict as good as the macro is because you have put, not you, so generic person, we have put the macro in the boundary conditions. So it is actually cheating. There is a level that doesn't come from the bottom. It literally comes from the. If we go to the water tank flushing device, the only reason why the hydrodynamics give you the same output as the logic of flushing is because we put something that is essentially irreducible, which are the geometric constraints, which are macroscopic. Without them, you don't get the flushing device. So you're putting all the macroscopic causes, you're putting them at time t equals 0. So my feeling with these methods, which I think are very powerful and great, is that they aspire to get only half the picture. They leave outside something that I think is very important, which is irreducibility of causes that exist, literally. There was a final thing to that, but my mind went off, so I will stop there. But otherwise, I think it's super valuable. Oh yeah, I wanted to say, I feel that it is like trying to solve the problem with your hands tied to the back. We are not really embracing irreducibility. And that's my whole feeling about these approaches.
Yeah, thank you. Very good point. So it's very funny. Every time I give this talk, I get two complaints on two sides. On one side, some people like you, very in the right way, say, I don't think the second approach is emergence because you're just saying the macro is enough, but there's nothing extra in the macro. There's nothing in the micro. And that's not emergence. That's one type of answer. The other answer is to say, I don't believe in the first one because the first one, the division into parts is from the observer, it's not real. So it's in the eye of the beholder. So emergence is just in the eye of the beholder. So it's not real. So either people like the second one because it's a bit more humble or something, or they don't like it because it's too humble and they want something. And I am with you. So I like both for different reasons. I feel that the first one has a bit more abstraction to get something extra in the macro from the micro. I think there are other ways to get something from the macro that is not in the micro that are we need also them. So that's why I said that. I don't think these two are the only ones. But I tend to think that there is no free lunch. So there is always the more you get, the more you're putting in somehow. And in my view, what we have to do is to build this framework so that it's very clear what are we putting in and what is the price we have to pay in order to get something out, and then we can choose: are we willing to put price in to get that, or I prefer a framework that is a bit cheaper, so I think I need to put less in to get something out, and then everyone can choose what feels right to them and get a conversion. But I agree with all the points.
Yeah, I was going to say, I agree almost everything with what Luis said and what you have just answered. And I have this doubt, and I think I maybe have an explanation for what's going on here. So imagine you have a container with a gas, and then you have the micro level, which are the particles, momentum, and all that jazz. And then you have this ideal gas law, P times volume, or whatever. So you think in terms of information theory, when you have this gas, this random walk going on, basically you have information dissipation because basically everything is converging to the central limit theory about the Maxwell distribution or whatever. But in principle, you're saying that you have the same information at both levels, so you're not gaining anything from the level. But to me, there's some kind of cheating there, which has to do with boundary conditions, has to do with the idea that you're putting information at the macro level when you're saying that you have walls. Because when we talk about this emergence, we think that the gases are in an infinite container, but they are not. So this P times volume, blah blah blah, law emerges when you have a container. And this container has walls, and then interactions with the particles with the walls are somehow the information that you have missed through this central limit theory. So I'm not saying that what you say is wrong. I'm saying that this hierarchy, there's no free lunch. So basically, you have to be putting something in the macro level that recovers all the information dissipation. In the thought experiment that you mentioned, that you have this random walk in different color communities, and then you have the upper level. Basically, you're putting color there, and that color somehow is something that at the meso level, let's say, this grouping is the information that you are adding to describe that. So what I'm trying to say, from a Bayesian point of view, let's say, is that you put some additional information coming from the description of the problem itself, and I think that solves somehow this parental paradox of emergence. So emergence, I think, is real. Causality at different levels is real. But because we as observers, as scientists, we are subjectively putting some additional description of the system in order to regain all the information that we have dissipated. I don't know if that makes sense for you. I would love to hear about your
That makes sense, and the point made that all the sort of boundary conditions are not included in the picture. It's a very good observation, and there's a way to include them. I will be very happy.
Okay, thank you. Just maybe to contribute to this discussion, what I think I missed a bit is that often, at least in context of thermodynamics, we speak also about conditions. So thermodynamics works amazingly in many circumstances, even when it shouldn't, but there are cases where it breaks. You cannot describe Knudsen gas with thermodynamics and so on. There are other examples where it just breaks. Or if you want to describe system in equilibrium, you need one set of observables, but if you want to describe non-equilibrium steady state, you need something more. So even if you come up with some recipe for macroscopic prediction in one task, you may fail to generalize. Or if you trained your neural network to distinguish cats and dogs, and then you show it a car. So there are some, so I don't think that it's a cheat. It's just a lack of discussion of what are additional conditions that make this approach work. And one more question. So if we consider very primitive dynamics, like system in equilibrium when nothing happens, is there synergy and emergence in that case? So equilibrium system, thermodynamic equilibrium system, does it have synergy?
Other question? I don't know. I don't know. I mean, what I like of this is that they, at least, especially in neuroscience, all the discussion about emergence or philosophy is all about moving your hands with a lot of energy and convincing people or whatever. But what I like of this is that this gives you a very concrete framework that you can test from data. I was also very interested in having something that you can use with data. And then, from my perspective, this is a very pragmatic thing. It's like, is this framework useful for your data in order to get some conclusion that is useful or not? And so I'm not so interested in solving the. I mean, I'm super interested in the theory, but I feel that at some point the theory has too many degrees of freedom and just have to put it in circle. And to the degree you can use this for practical applications, you start getting a feeling of what you can do or what you can do. About the point you made about, so to answer the question, I don't know, but I would like to compute it. You know, you have a concrete example, you can measure it, and then you can find an empirical answer to that. About the first point, something that is important is that a coarse graining is closed or whatever only for specific probability existence. So you can have the same system with some parameters, and maybe for some parameter values, that coarse graining is good, but then for others not. And one thing that I'm very interested in is what you mentioned about generalization. So if you get one coarse graining that is good in some conditions, how can you predict that this is going to be good in other conditions also? And about the learning thing, I have the theory that maybe there is a way when you're training an algorithm to control how deep in this hierarchy the agent will learn. And if you don't learn so deep, I think you will have better generalization, because if you have a new process that shares the abstraction, but the micro is different, if you only learn up to the abstraction level, then you should generalize well. So there's a lot of questions in this space that are not answered, but they are super interesting. I agree.
Okay, thanks for a very nice discussion. I think we should move on. Let's thank Fernando again. The next speaker of this morning is Carlos Gutierrez. He's going to talk about engines with thermal feedback.
Well, first I want to thank the organizers for accepting my presentation. It's the first time I'm gonna talk in a seminar, so I'm very excited. So today I'm gonna talk about equations of motion for heat engines. I think this seminar is for tools and methods for complex systems, and that includes living systems. And I think we can not ignore that living systems function by engines. There are engines in many different systems. So first, I'm gonna start with the motivation of the idea for trying to study equations of motion for heat engines. So first, what I'm describing as an engine. I'm saying that an engine is an open system that output works powered by an external disequilibrium. So for example, we had a heat engine. A heat engine, we had a temperature difference, and from that we can make an engine that makes some work. So I'm going to say that the engine makes some active work, and to that active work is related an active force. And an engine should be an irreversible system. There are two types of engines. There are chemical engines that are driven by matter exchanges. So one example of these are electric motors. In electric motors, there are charges at a difference of potential, and an engine can use that to produce some work. For chemical engines, there are like better descriptions. We have a better idea of how they work. But for heat engines, there is a lack of dynamical models. When we take a course of thermodynamics, we learn about engines, but we think about them that we say that they are always quasi-static processes, and we don't talk really about the dynamics. When we take a course of thermodynamics, the time never appears as a parameter. So there's a lack of dynamical description of what is happening in it. That is related to someone that Russell said some time ago. That is that there are theories like that describe workless dissipation. So, for instance, in statistical mechanics, we can talk, for example, about the Langevin equations, and we can talk about dissipation and talk and get like the we can write the Fokker-Planck equations and talk about how what happened with systems that are dissipative and are non-equilibrium systems, but are going to a equilibrium state. But in an engine, if we maintain that it's equilibrium, it is not going to an equilibrium point. And there's like a couple behavior between the parts, the thermical parts and the mechanical parts of the engine. So it's quite different. But we should point out that there are like what we are calling kinematic models. So even when we don't have good dynamical description of what is happening in engines, we have some models for explaining what I'm calling kinematic models. I'm gonna show some examples that probably you all know. The first type of kinematic models is anti-damping models. So the main example probably is the van der Pol equation. So in the van der Pol equation we have some linear anti-damping and non-linear damping, and that produces a limit cycle. So we are not telling anything about what is happening thermically, but we can have some model about like having limit cycles. The engine should be a self-oscillator because that, what that means is that the external disequilibrium doesn't have any frequency, but the engine should go to a limit cycle and have some periodicity. And that is something that we could describe with this type of model, like the van der Pol model or other similar models, like the radius oscillator, smaller than that. Other examples are circulatory forces. I'm not so familiar with this kind of model, but the idea is kind of adding forces that drive particles along potentials. There are predator-prey models, like Gustavo Terra. I'm sure you're all so familiar with these kind of models. These are more like related to chemical engines, but they're common. There are time delays. We can describe engines trying to use time delays. There's a model of vocal cords that explain how vocal cords can be related to time delays. And if we take some time delay equation in some regime, we can do an expansion and see that it is like equivalent to having an anti-damping model. We have periodic pumps and we have maximum demons that are equivalent to clumping. And we see that sometimes for describing biological systems, these are models that we often use. And they are like lacking information of what is really happening thermally. But these are the models that we have. So to to motivate what I'm going to do later, I'm going to try to distinguish two types of non-equilibrium systems. First, we can talk about passive models. What I'm referring to passive models is systems, systems that only are only dissipative. So we have some free energy, some high free energy that go into a low free energy, but it is only dissipative. That's what we can describe with statistical mechanics and what we really know. But we don't know too much about active systems. So we can use the dissipative process to add mechanical degree of freedom and use that to use them as an engine. An example is to add a turbine and make a pump with that. So engines can work by turbines, by pistons. It can work in many different ways. I'm going to focus in piston engines. So how a piston engine works. So let's say we have some generical piston engine which have an equilibrium at x equals 0, and that equilibrium is, we're going to say that is stabilized by thermal feedback. So if I move the piston, it will start a thermal feedback and the system will go to a limit cycle. And for understanding what what should happen to the engine in order to work is that, let's say the engine has no temperature. Later I'm not going to talk about temperature because I don't like that. If we are describing a system that is not in equilibrium, I think we should not talk about temperatures. But at the moment, let's think that we have that the working substance of the engine is have some temperature. So we describe that by the mean temperature and the temperature difference. What we know about engines, like for instance, let's think in the Carnot cycle. The Carnot cycle is supposed to be the most efficient cycle. And what happened in the Carnot cycle? That it happens that heat exchanges happen at maximum temperature and minimum temperature. Well, thinking about Carnot cycles is not that useful if we are trying to think dynamically, because Carnot cycles only function if we think that the system is quasi-static, and that is not very realistic. But we can translate that as to what really happened as thinking that the temperature should be in phase with the heat exchanges. So that is the main idea that I'm going to use to trying to write a simple model for how to describe heat engines. So the idea is use non-conservative analytical mechanics and trying to understand what is the active force that I'm talking about. So for doing so, what I'm going to say is based on this genetic heat engine, I'm going to propose that this equation. That what I'm trying to say with this equation. Notice that at this point I'm not trying to say nothing about temperature or entropy of the working substance. I'm just trying to think what is happening with the heat, what is happening with energy exchanges, because that's what we can study. And the idea of this equation is that if we fix the piston position, it's at the equilibrium point, but we somehow let let the heat exchanges happen, what it will happen is that the same heat that enters the system leaves the system, and there's no work. So the idea is that in order to function, the heat engine we should take into account the modulation that the piston is doing in the heat exchanges. So with this equation, we can use the first law of thermodynamics, use integration by parts, and we can get some conditions. So this function that I call theta is what I'm calling the modulation function, because what it means is how the piston position make the heat exchanges, how the piston position modulate the heat exchanges. So if the engine works. So this modulation function, I guess that it should be a linear function in x, and we have that the active function from the equation that I proposed have to be the integral of the heat exchanges times this modulation parameter plus a constant. But adding a constant term to the active force doesn't seem to make so much sense. So I'm just taking it zero. So I have now this equation for the active force. I'm adding a generalized coordinate cube for the example that I'm going to use later. And now the idea is that I can plug this active force into a functional and minimize it and get the equations of motion for a piston. But now I have a description of what is happening with the internal energy of the working substance. And now I'm saying something about how heat exchanges are happening, and I'm telling you what is the active force. So I have a better idea of what is the active force. And something that I want to point out is that this kind of description of the piston and the working substance are coupled. So we have thermal things in the functional that is described in the piston because the active force is depending on how heat exchanges happen. So in the functional of what is usually just a functional of the phase space of where we are trying to describe, now we have thermal information. And in the information of heat exchanges, we are including the mechanical degree of freedom. And that is something that I want to point out. You can think my model is good or is bad, but something that I want to point out is that somehow it should be coupled. We should couple the equations of what is happening thermically and what is happening in the mechanical part of the engine. We cannot just tell something about the thermal part and something about the mechanical part. We should mix the parts, and that is where we are thinking that it is kind of the problem of why we have a lack of dynamical descriptions of heat engines, because we usually don't think about coupling these kind of equations in this way. And I want to point out that this model should not be valid near the equilibrium because it can happen strange things. But probably I'm going to say something more about this later. now I'm going to use some examples of these problems. So this is a Stirling engine, and I'm going to try to use the mode that I'm presenting. So to get equations of motion for this Stirling engine. So let's say we choose um, the generalized coordinate by this angle, um, and with that we can use analytical mechanics, and we can write down the kinetic energy if we know how the piston position works and the. Well, let me explain first how is this engine working. The thing is that the heat exchanges are controlled by the displacer that is the white thing that is in the lowest part of the engine, and the engine then have a piston that is modulating the heat exchanges, and both are connected to what we call a flywheel. So if we know the displacer position and we know the piston position, we can write down the heat equation, we can write down the kinetic energy. With the heat equation, we can get the active generalized force, in this case, torque. And with that active generalized force, in this case is interesting because why, like, for this degree of freedom, we can integrate the force that not usually happen, that happen because we're using an angle. And I can write down a Hamiltonian for the system. The thing that with this Hamiltonian is that first notice that it includes thermal information about the system, so it's not truly a Hamiltonian. It is not only about mechanical things. And this Hamiltonian is, if we take the angle as a non-compact variable, is unbounded from below, and it's similar to what happened for when we write down a Hamiltonian for the RC SJ model for the Josephson junction. That is another active system, and we can write a Hamiltonian, but it happens that it is similar to the Hamiltonian, which is unbounded and is kind of weird. This is the solution if we take the Hamiltonian, get the equations of motion, have some dampings and a restitution force. This is the kind of solutions that we have for large set of parameters. This is some example of some solutions. And now, why we will be interested in engines? Why will be interested in heat engines? Some example for a case of use of this kind of mode is that maybe we can relate this with the precision of flux. Precision of flux, there have been many studies of precision of flux. So I'm going to hit this. And the idea is to try to add noise because in reality I'm saying that the heat exchanges are like exact, but they should have fluctuations, and if we add damping, it should be fluctuations by the fluctuation dissipation theory. So in this example, I can add some noise to the equations that I get for the Stirling engine, and I can do an analysis by averaging over a cycle and trying to get an equation for the phase velocity and looking what is happening with the diffusion term, with the noise term. And we can talk about what it will be, but what it will happen with the precision if we take the Stirling engine as a clock. and how it could be related to energy productions per cycle, I'd say that I'm not talking about temperatures or entropy, but that is for the working substance. The reservoirs or the thermal baths that are connected to the engine, they have a well-defined temperature, so I can talk about entropy production if I know what are the equations for the heat, and I can know what is the heat dissipated in the living cycle, so I can relate that to how to what happened to the precision of the Stirling engine functioning as a clock. And why will we care about that? Well, the reason why I'm talking about this is because there are there's an interesting problem in what happened to biological clocks, and there's a studies of what happened to the cost of free energy of biological clocks. But these studies are kind of uh, mixed between experimental results and analytical results, where the analytical results are based on these kinetic models. So we are trying to get a very dynamical description of what is happening in clocks, so we can have a better understanding of this kind of analytical analysis. Because if we are using these kinetic models, well, it models the system, but maybe we're losing information of what is really happening. We are not really understanding the physics behind these biological clocks. We are just using a numerical equation to try to study what is happening with them. So that's the main point that I wanna do. That is that I wanna, yeah. Like the take-home message from this is we should think more about engines. Engines are important, and we usually don't think too much about them. We just um, think about it when we take thermodynamic courses, and we don't have really a good intuition of what is really happening in engines. And I think it's really important in biological systems to start thinking about engines and what is really happening with when we talk about active systems and things like that. And I think that is all I have to say.
I think we have time for a question.
Thank you for your presentation. Are there any plans to apply this type of analysis for engines that don't use piston and that would use cycles with phase transitions, such as maybe a Rankine cycle?
It will be interesting, but I'm not trying to do that yet. I'm not very familiar for how turbine engines really work, but maybe in the future it could be interesting. That is part of the point of the presentation, that at this point we don't know too much about engines, and we should start thinking more about this kind of things. At the moment we don't have a model for the other kind of engines, but it will be interesting for sure thinking about it.
I guess I have a question myself I didn't really get. Um, what system should I think about when I think about the biological clock? Like experimentally, what is the biological clock?
In biological clocks, well, I'm not an expert, but um, this in this reference, there are several uh, examples that they mention. Some example that I remember is biological clocks in the context of eggs of frogs, I think. And the thing is that they are like uh, activation and inhibition of some molecules that regulates the mitosis in frog eggs, and that is that is the example that I remember from this paper. But there are several examples like circadian uh, cycles, and there are several examples that maybe in this paper there are plenty of examples. Some of you are interested in
I think we have.
Do you think your theoretical models can be applied, for example, for ionic channels in the membrane of the cells, for example, active channels, or ionic pumps?
I'm not really sure if you're yeah. Yeah,
Okay.
I'm not really sure, but Alejandro is more interesting in that kind of model. So
Okay, I think we're running a little late, so maybe next speaker can start coming. Carlos again. So the next speaker of this morning is Stein van Voren, and he's gonna talk about icing machines and other optimizer.
Thanks for having me. So today I would like to talk indeed about icing machines and how we can improve them. And on this project I'm working together with Guy van der Sande and Guy Scaffold in the Applied Physics Research Group in Brussels. So first I would like to give some motivation. So as found in the study, about 10% of the worldwide electricity usage is due to computational demand, which is huge and is growing. It's even projected to become 20% by 2028. And also, we're coming to the end of Moore's law. So classical CPU architectures are not improving anymore, or slightly at least. And so, why icing machines? So they can do many things, but today I want to present them as optimization solvers. And one such example of an optimization problem is the traveling salesman problem, where you have a bunch of cities and you want to find a tour which minimizes the distance. So you want to visit all of them in the least amount of distance. And if you look at the number of possible routes in function of the number of cities, it really explodes, and it's an exponential function. So it's a really complex problem, basically. And so in general, optimization problems, they run for very long times and require massive amounts of resources to solve. Some examples are network and resource optimization, scheduling, knapsack problem, for example, cargo loading, and there's plenty of them. There's really a large demand from industry. And so there's a need for faster and more energy efficient computing, and this is something that natural computing aims to solve. Now, what is natural computing? So in terms of optimization problems, so first off, what is an optimization problem? In optimization problems, you have a cost function, so basically a function, and you want to minimize this function. Now, then we build a physical system, and this physical system has a certain energy, and we design this physical system in a way that this energy is the same as the cost function which we're trying to minimize. And then this physical system is an energy dissipative system, so it tends towards this lower energy state, and then this lowest energy state or low energy state
is read out as a solution to the initial problem. And Ising machines are natural computers. And with Ising machines, we map the cost function which we want to minimize onto the binary Ising energy, where you have basically a network with spin values on the nodes, which can be either -1 or +1, which we call spin down or spin up. And then the weights of the network, we call in the context of Ising machines the interaction matrix. And then the energy of the system is given by this matrix product, together with factor multiplication of bias, in which we can encode boundary conditions of our problem. So, for example, if you come back to a traveling salesman problem, and I will give gross oversimplification here, but we can put spins on each city, which can be either spin up or spin down, and then we encode the problem into the interaction matrix, which in this case could be the distances between each city. But we want to build actual physical systems, and in my talk I'll be talking about analog systems. And for analog systems, we have continuous dynamics. So the spins, instead of being binary, they are continuous. So in this case, the spins are real valued numbers. So we have a continuous energy, but of the same shape as the Ising energy. But this continuous energy is not equal to the binary energy. And that's an issue because you're trying to solve a binary optimization problem, which takes binary spin values, right? So in order to make this analog system behave in a binary way, usually what we do is we introduce nonlinearity into the system. And this forces these continuous spins into binary values. So basically, this results in a pitchfork bifurcation for the spin values, such that they tend to steady states of plus and minus some value. And then the energy is minimized. These Ising machines, they are energy dissipative, and the lowest energy state is read out. And we retrieve the solution to our initial problem, which is a binary problem, right? By taking the spin of the sign of the analog spins. So all the positive values are spin up, the negative values are spin down. Right? So, and how do they minimize their energy? So classical analog Ising machines right now, their dynamics resemble those of gradient descent. And with gradient descent, we have, you can see that the particle in motion going to low energy states, and the velocity of this particle is given by minus the gradient of the function to be minimized. The function to be minimized in case of Ising machines, so it's the continuous Ising energy together with the nonlinearity, as can be seen on the left here. And in this case, I'm showing you a double potential law, which we add to the energy, and this makes sure that the spin values are deepened at minus and +1, and the energy is raised elsewhere. So the spins converge to minus +1. Now, let's say we have this function to minimize. So what do the dynamics of gradient descent look like? For example, if you start here, end up in global minimum, which is great, but it's dependent on the initial position. So for example, here we end up in a suboptimal solution. And what we do usually in classical Ising machines is we add some noise into the system, such that we can avoid getting trapped in local minimum. And then, for example, here we're getting out of it, which is great, but it has some disadvantages. So what do those dynamics look like? Usually, so here I'm plotting the analog spin values of such an Ising machine in function of time. Basically, they get initialized to 0, and then they tend to some steady state, and the solution is read out by taking the positive values as spin up and the negatives as spin down. Right. So many physical implementations of Ising machines exist. We can put them largely in 4 categories. We have binary ones and analog implementations, and we can subdivide them further into electronic and into optical ones. And today I will be focusing my talk on the analog implementations. And here I also just want to show that many of those physical implementations exist. And yeah, let's take a look at the slides. So now, what is the key message of my presentation that I want to give to you today is that all those analog Ising machines, they're based on gradient descent. But gradient descent has some issues, and we know that stronger optimizers exist. For example, if we look at machine learning, we have momentum and atom optimizer, which have largely transformed fields and largely outperform gradient descent. So why would we not port them to Ising machines? And this has been studied in one paper already, where they made an effort to combine momentum and atom optimizer with a very specific type of implementation. And in this paper, so they did it for one single physical implementation, simulations of it, and they ported the momentum and atom optimizer in a discrete way and for a single nonlinearity. But our goal is to generalize these results, and we want to perform simulation that holds up for any type of analog system. And also we wrote down continuous versions of atom and atom optimizer, paving the way towards actual physical implementations, because those analog systems, they're continuous by nature, so those discrete optimizers, they don't tell you at all how to implement them physically, right? And also we studied the influence on performance of multiple nonlinearities. So first off, on the left side here, I'm showing you the discrete updates rules as known in literature from momentum optimizer, and then our continuous adaptation. And for momentum, it's actually very straightforward. You can see it as a heavy ball rolling with friction. And if you would discretize this system in first order, you would retrieve the update rules as known from literature. So that's pretty straightforward. And as you can see, you have this velocity here, and then we have a momentum and a friction term and a damping factor here. So what do those dynamics look like? Now if you compare it to gradient descent. So as you can see, when the ball rolls downhill, it carries momentum and it can travel uphill again, compared to gradient descent, which can only go downhill, right? And in this case, we end up in global. But there's still a disadvantage. For example, in this case, it needs to build up its momentum, so it can be rather slow to converge towards a solution. And this is where the next level of sophistication comes into play with atom optimizer, which it also has momentum, but now it also has an adaptive learning rate. So it helps build up the momentum while rolling downhill. I cannot get into too much detail, but these are the discrete update rules that's known from literature. And we wrote down this continuous system here, and again we inspired ourselves by the discrete update rules, such that if you would discretize this system, you would get something very similar to the one known from literature, but you have to make some approximations and some substitutions, but either way the general structure is pretty much the same. So again, we have a momentum term with friction, and now we also have this adaptive learning rate here in the velocity. And this adaptive learning rate is large in the beginning, helping the system to acquire momentum, and then it tends to 1, value 1, where it is again the same as momentum optimizer. And we wrote down 2 versions of this continuous system, and the first one has an adaptive learning rate, which is exactly the same as known from literature. And then we also make a first order approximation of this function, which evaluates to the inverse square root of time. And the reason that we did this was to hopefully be able to implement this function, because this function known from literature is pretty complex to implement in a physical system, for example in an optical system. So we made this approximation in hope that it's easier. But actually it turns out that it also outperforms classical programming, and for a reason that we'll come back to later. So just some terminology. With this adaptive learning rate, we call it atom Ising machines, and with this one, we call it first order atom Ising machines. So what does atom optimizer look like? So now in this case, again, where momentum had to build up its momentum, and it happens rather slowly, atom does so quicker. Okay, great. But it's pretty anecdotal, so let's quantify the performance of each type of Ising machine and compare them. So these Ising machines, they're non-deterministic systems. We start each run from a different initial configuration, and we also add noise to the system to avoid getting trapped in local minima. So we need to do multiple runs and statistically analyze their performance, right? And what we've done is we've done very large, we've done many simulations on benchmark sets, specifically Quick set and G-set, which are very popular amongst Ising machine scientists to compare results. And we've run about 5 million core hours of time on the supercomputer to compare the performance. Some metrics we can look at are, for example, the success rate, which is a percentage of runs that reach a certain target energy. And then, for example, from this you can compute the time to solution, which intuitively is the time required to reach a solution with 99% probability. So basically, the lower the time to solution, the quicker your Ising machine is, right? And also an interesting one is to look at the solution quality, which you can do by looking at the percentage of best known energy that an Ising machine finds. So these benchmark sets, the theoretical ground state is not always known, so we're actually competing between everyone, well, not competing, but finding best known energies all together, and then we can look at which percentage of this best known energy we can find. Great. So also, these Ising machines, they have plenty of parameters, fine-tuning parameters, and their performance heavily depends on those parameters. So usually what we do is we compare different types of Ising machines. Is we run for a bunch of parameters, we take the best value, and we compare only the best values of those Ising machines to each other. For example, you can do so by grid search, for example here with 2 parameters, but in my case, for our simulations, we're actually doing a second level of optimization, and we're finding the best parameters by Bayesian optimization. Great. Now, I told you that we use nonlinearities to enforce some binary behavior in our continuous system, and it turns out that not all nonlinearities are created equally. The performance of your Ising machine also heavily depends on the type of nonlinearity that you pick. And in this paper, they studied 4 different types of nonlinearities for classical Ising machines, so what they build now, which are all based on gradient descent. And he finds different performances, and it's also exactly what we did for the new types of Ising machines that we introduced. And we check all of those nonlinearities as well for the new Ising machines that we introduced. And please don't be scared about this table. Please don't start reading the numbers as well. I will ease you into it. So what we see here is in each column we compare different types of Ising machines. So the gradient descent based types are the ones being built now. Then we introduce the momentum and the atom ones, and then for each one we look at the 4 different nonlinearities. Now we can look at different benchmark problems, which are seen in each row, which is a different benchmark problem, and then we can compare the time to solution here. So basically, the lower the number, the quicker it is. And green one is always the quickest one for some problem set, and red one is the last one. And the take-home message here from this table is that first off, atom always outperforms the other types of Ising machines. And also, if you compare nonlinearities, you can see that the sigmoid nonlinearity is always quicker within each class of Ising machines. And this is also supported by a bunch of other data, but I'm just presenting you some examples, right? And then, so from now on, I'll only present the sigmoid nonlinearity as it's the best one. And we can compare the best known, well, percentage of the best known solution that those types of Ising machines are reaching. And as if we look at, so we look at different benchmark problems again. So each set here is a different problem. So if G6, G7, and so on are all different problems. Then in blue we have atom types of Ising machines. In light orange we have first order atom. In green gradient descent, and then in orange momentum. And basically what we see is that the first order atom types of Ising machines, they reach 100% of the best known solution in literature each time for these problems here. And we found that even sometimes they improve on the best known solution. So it's like kind of like unlocking a new high score, which is great. And then in these bit more harder problems, we see that first order atom keeps up fairly well, and they stay above 99.7% of the best known solution, which is also great. While atom Ising performs a bit less, and then even worse, gradient descent types Ising machines, again, which are the ones being built right now, they only reach 97%, which in optimization terms is actually a huge difference, 3%, because the closer you get to this 100%, it gets exponentially hard. Okay, so great. The solution quality of First order atom Ising machines are way better, but we can also look at their speeds, and this we can measure by the time to solution, which I show here. And again, these are all different problems, so G1, G2, and so on. And we normalize the time to solution such that the fastest one is set to 1. So basically what we see already is that first order atom is fastest in each instance that we analyze, and also again for a bunch of other data it's every time quickest. And we see that all the other methods, all the other types of Ising machines are 10 to 100 times slower. So not only does first order atom Ising machines reach better solutions, but it's also a lot quicker, right? And now, why is it that those first order atom Ising machines work faster? We wondered. So again, to recapitulate, those atom types, they have this adaptive learning rate, and here you have to take this beta 1 and beta 2 between 0 and 1, because this function puts constraints on those two constants, while this, for first order atom, this first order approximation has no such constraints. So the value of this constant can be taken any value. And so this beta 1 and beta 2, which are also in these two equations here, can be taken to any real value. And if we take them negative, or as large negative numbers, it actually significantly speeds up the dynamics of these two equations, such that the machine converges quicker to solutions. And also, we decoupled those two constants, so we have an extra degree of freedom, such that our system can adapt more to the problem, and we can fine-tune it even better. So those are two advantages. So far I've only showed you simulations of actual physical systems, but Ising machines, or simulations of Ising machines, they actually compete with state-of-the-art optimizers. So we can also ask ourselves the question, how do those new types of Ising machines we just introduced compete algorithmically? And so the only difference here is now that when you discretize the system, you can take the time step arbitrarily, while for the continuous physical systems, you have to take them sufficiently small in order to reflect the continuous nature of the machine. And now you can also actually optimize this discretized time step. And okay, I can show you a bunch of results, but I think I'm running out of time. So basically what we see is that the time to solution is pretty similar for all types of Ising machines. So you don't gain a lot of time, but it's first order atom Ising machines, they reach somewhat better solutions, but the difference is not as big as for the actual physical systems. So yeah, algorithmically, it gives some improvements, but it doesn't seem to be as huge as for actual physical systems. And I showed it here. Okay. So the importance really lies in physical systems, right? So how could we implement them? Actually, for some classes of analog Ising machines, which are kind of semi-analog Ising machines, where we have some conversion from analog to digital and back, and where the feedback is computed in classical type of architecture, for example in FPGA, it's fairly straightforward. So you just have to make some software adaptations and exchange the gradient for now the atom terms. So here it's actually fairly easy, but those types of Ising machines, they have some issues in my opinion, and would love to go completely analog. This is really where the money is for Ising machines, I believe. And here it becomes more complex. And for a momentum term in an optical system, we think you could maybe do it with a bandpass filter. For the adaptive learning rate, it becomes more complex. So we don't know, maybe a complex bandpass filter, but it seems hard to do. We don't really have any idea. But at least the first order approximation seems to simplify things and open some pathways towards implementation. Right. So to conclude, we studied nonlinearities. We found that the sigmoid one works best. And if you look at physical implementations, the first order atom Ising machines are 1 to 2 orders of magnitudes faster than gradient descent Ising machines, and they reach better solutions consistently. While algorithmically, okay, they're as fast and they reach somewhat better solutions, but it seems less interesting. And also something we found, but I need more data to support this, because we've done the simulation, so I hope you can believe me, but the gap in performance grows with increasing problem size and difficulty. That's a bit too much to show in this slide. So basically, first order atom scales better with difficult problems. So for real world problems, it would outperform it even more. So it might be worth looking into physical implementation. So thank you. I would love to take some questions.
Thank you, Stan.
I have a question about, so instead of going from binary problem before going to continuum spins, could it be possible to use POTS models where you have discrete values but sufficiently many so that you can have different states of the spin? If you understand my question.
I didn't hear quite all of it, but so
Okay.
you're talking about the conversion from binary problem to the continuous problem to spots model, or
Yes, so
yeah.
instead of using the continuum value, you could use, I mean, rational value, for instance,
it's
where
possible, and such implementations also exist in the binary part of those ISO machines. I'm not an expert on it, but yeah, indeed you can also stay in the binary world and well, make physical implementations. Well, they exist, but yeah, we mostly specialize in analog systems as they are more energy efficient and they have bigger bandwidth. So, but yes, some of those implementations also exist. Yeah. And actually, to come back to that, also one of the reasons why analog also has positive compared to one of those implementations is that often the path in solution space becomes easier when you make stuff continuous.
What about the performance of these algorithms when you have? So, if I correctly understand, you check the performance with some data set problems that are in the literature. But is some way to check, for example, how depends the performance with the height of the barriers between attractors or all these facts that can happen in a real problem? This is one thing, and the other question is related with the these algorithms that we can find almost every day. There are new algorithms that try to perform better than the other. When I have a paper that can to refer this paper, I saw as you already said, this is a very tiny difference in performance. My question is also computers are developing anytime and they are going faster, so it compensates developing a new algorithm that has a so small difference in performance with the speed of a new computer or the power of new computer that, of course, also all days are developing. This is the question.
Okay, thanks for your question. I'm not sure if I understood completely, but to answer your first question, there are some theoretical analyses, but mostly what we study are just benchmarks because it's a very complex system, and right now it's more of a pragmatical approach, I would say, and we come up with new ideas, we test them, measure some stuff, and that's it. But it could be interesting to look in detail attractors and so on, but I'm not familiar with this type of work, and I don't think it's done actually very often in the field. And then to your second question, so if we look at, well, indeed, architectures, classical CPUs and so on, they're still increasing in speed and so on and in performance, but the increase is marginal. Well, as I showed in the beginning with the end of Moore's law, increase in the beginning, it was really huge, like 70% increase in performance yearly, while now we're only going to 3.5% increase yearly. And we have very large increasing computational demands. And actually here, for example, in optical implementations, we're not looking at 3.5% increase, but increase of 1000% or more in bandwidth. So that's really different level order of magnitude increase. So even if algorithmically you don't see an increase, just your hardware itself is giving most of the increase in performance. I don't know if that answers your question.
Well, this is just an example in my research history. I started so many years ago, for example, integrating differential equation with Euler methods, very very optimized method. Then I passed to Ranjikuta method, for example, and then now I still program with Euler method because I have a very powerful computer. So although the method is it's not very powerful, the algorithm, but the computer is so powerful that I can run my simulations even for very large uh, system size. So this is in this direction is my
Yeah, okay, but yeah, I see your point, but again, I think maybe I should show what I mean. But yeah, I see your point, but so I think it also depends on over which period you're looking. So indeed, if you were using Winchkuta in 1988 and you compare it to now, yeah, okay, it's 10 compared to 10,000, so it's 1,000 times faster, right? But if you would compare in next 5 years, it would not even be twice as fast. If you look at the difference in hardware acceleration. So we're really looking at alternative types of hardware which do give this exponential growth again. And that's really the motivation behind natural computing, is to look at alternatives such as in optics, for example, where we have way higher bandwidth than for electronics. And so we would again see this increase of 1,000 times at least in performance.
I think we can leave further discussion for the coffee break. Thank you, Stein, again. And a quick announcement, if you're a speaker of this morning or especially this afternoon, please make sure to send your talk to Joaquin or put it on the computer that is there. Yeah. Especially for the afternoon session, because yeah, we're not going to be able to accommodate. And maybe let's reconvene at 11:30. It's yeah, 11:30.
So problem is you have movies on Mac, no?
No,
It's a Windows.
no. I think it should work, no problem. Like, just a bit. But I don't even know.
That's good. Yes, if you have this board,
Yeah. So
no,
I
I
don't
think
know.
this will be no problem.
Oh,
So it's no problem.
okay.
Just to check everything is working. Yes, so nice to meet you. So thanks for coming. Everything was okay.
Because last time I arrived so late and the question
No problem. Yeah, you are coming with us.
no, I was going to come, but then it's complicated.
Yeah. It's complicated with child. For me, it's the same. Simple enough. Everything is okay. If the hotel is okay, if the ticket for the flights are okay, so it's okay. Okay. So enjoy the rest of the meeting. Okay. No, bueno, es un
es corto con años, ¿no? Tengo las
Sí.
presentaciones, pero
Bueno, aquí hay algunos, no sé si es esta de aquí.
esa es.
Esa es esta, ya está.
Lo único que quería comprobar si era posible,
Sí.
que tenía muchos vídeos.
Sí, entonces los...
En PDF, no sé si podría dar problemas. No sé si es posible con ¿Sí? Lo tengo en el
Pues ponlo y lo chequeamos. Lo chequeamos en un momento.
Sí, no te preocupes.
Show good?
Ah.
O sea, ponlo aquí en el...
Sí.
Como aquí para...
I mean, if you are like... Yeah, I already finished. It's working, yes.
Perfect. So leave there in the desktop.
Hay una cosa ahí, no sé si...
Here is yours. So then I will open my email. So please don't remove anything in my email. Nada. So you are yes, okay. Nice. You are from Amsterdam. Ah, nice. So I was working in Nimega in Nijmegen. Yeah, with Professor Kappen, Hilbert Kappen. Yeah, he's from machine learning. I have a friend also in Amsterdam. It's Jorge Mejias. He's working in science. Yeah. Very yeah, is this the name?
Yeah, I think so.
Yeah.
Just
Just open and
now you can close.
maybe you can see it. No, problem. I have nothing to hide. Okay, so I don't know how to step to customize your yes, yes, this works. Yeah. Okay, I'm going to take a call. Yeah. Okay.
Hello, welcome back. Apologies for starting late. This second session of the morning. And the first speaker of this second session is not me, it's Wout Mervis, and he's going to talk about Markovian spreading dynamics on complex networks.
All right. Let's just wait till everyone takes a seat. Okay, so welcome back, everybody. My name is Wout Mervis. I'm from the Dutch Institute for Emergent Phenomena. So I'm going to start my talk with a little advertisement about the place where I work, because I think it's a great place fitting to this crowd of people as well, where sort of scientists from different disciplines and different institutes of the University of Amsterdam meet with an overlapping interest in studying emergent phenomena and emergent properties. And so it's a great place to visit because we have monthly seminars, and some of you in the audience have passed by as well, and they kind of it's kind of interesting to see that you can interact with mathematicians, physicists, ecologists, economists, and any kind of person that is interested in studying emergent properties through the lens of complexity science. Because when you start looking at the world in that way, you really kind of see that emergence is everywhere. It kind of permeates all scientific disciplines. It's happening in all length scales in nature, from the smallest scales where collective behavior and collective properties of electrons give rise to exotic phases of matter, such as superconductivity, to like larger scales where larger molecules self-organize to form living cells, and those living cells connect with one another to form great networks capable of processing information, leading to the emergence of intelligence, maybe even consciousness. And then you have these intelligent and conscious beings that interact with society, with one another, leading to the emergence of great cooperations, but also spreading the risk, posing the risk of spreading pandemics. And so part of my research theme is kind of like how can we use mathematical numerical methods from different parts of science, mainly from the top left corner here, quantum many-body systems and quantum information, to apply them to study complex systems and maybe in other domains. So I'm going to talk about important methods that were developed in that context of the case where everything is kind of nice and neat and you have regular lattices, but you still see these emergent collective behaviors, and importing those kind of techniques to things that are a bit more messy, where you have interactions on complex networks and maybe spreading dynamics for Markovian systems on networks. So what am I going to really talk about? Well, I'm going to talk about the sort of network dynamics. I will take that the network structure is kind of given to you. So of course this is very important to study, but I will suppose that the networks are static and don't change in time. And you are just giving some network, and you are posed with the problem that there's some dynamical system taking place on this network. And just so that we're all on the same page, I want to discuss a little bit like the different levels of description that you can have when you're faced with this network, and what I'm going to be looking at today. So I'm giving some network. It can be a complex network. Each node is a state, so actually it helps to think about a specific process, but of course the specific process can change. So mainly I'll be looking at some spreading processes, like the SIS model on the network, where each node is effectively susceptible, and there's a marked process going on, where if your neighbor is affected and you are susceptible with some brain beta, you can become infected. And then with another rate, gamma, you can become susceptible again, like a healing transition. And I'll also add the reverse process just to have some spontaneous infection so that the thing never dies out. The thing keep going forever. So suppose you have that, then my network actually is just the state of the system is just some coloring, right? So each state is a color, then I can have all possible colorings of my network, and that's the most microscopic description that I have. So my state space is a space of all possible colorings of the network, which is kind of exponentially large. But usually what people do is they say, well, maybe some nodes, I can take them to be statistically independent, and I get some mean field approximation, where this node-based dynamics, where I only have, the order of n, where n is the number of nodes, ODEs that are coupled to each other. And at the largest level, I can just take the collective dynamics, which is the average of the whole network, where actually sort of the network properties don't really play an important role, except that they kind of just renormalize the effective transmission rates. And so there's these three levels of description, and I really want to focus on the microscopic part. How do we describe this in analogy to how people describe many-body quantum systems, and how much of those exponentially large state space that we're looking at is actually relevant for the problem. How can we even figure that out? So let's just put a little bit of math formalism that will maybe be useful later. So if I look at the system at this most microscopic level, each node in the network, I can think of a little vector, right? So in the top components, maybe the basis vector of that node being susceptible, and the bottom component, the basis vector of that node being infected. And then the probability distribution over all colorings of the network, over all states of the network, that's a ginormous vector, which is summing over all possible configurations, and the configurations are just taking tensor products or Kronecker products of these basis vectors. And then the scalar multiplying that is the probability of the network being in that state. And then the process here is just some Markov process that takes place on this configuration space. But the key point here is that at this level of description, the Markov process gives some linear differential equation. So it's just a matrix that's also 2 to the n dimensional multiplying this large vector. And I can actually write that transition matrix for the Markov generator. I can write that as a sum of what I call local operators. So that's kind of important because the local operators, what they do, they don't act on the entire space. They act on the individual basis vectors that are inside the tensor problem. And so these are the local operators that act on one side. They implement the recovery transition and the infection transition. And these are the nearest neighbor ones. They act on two sides simultaneously. But the idea is that they don't act on the whole network. And so that's kind of similar to writing a local Hamiltonian quantum many-body systems, because we know from that example that when you have local Hamiltonians, then the exponentially large Hilbert space that the quantum system is exploring is actually a bit of a farce. So for local Hamiltonians, the ground states of these kind of systems are actually much smaller, and they can be characterized as sort of polynomially in system size. So the question is does that happen here as well? So how large is the effective kind of description? So we see here you have different dimensionalities of the description. Here you mainly have nonlinear ODEs coupled to each other, and here you have a linear system, but it's just exponentially large. The question that I want to address is what's the real effective size of the large distribution distribution? Can we compress it? How do you compress it? And how do you figure out when that is possible? And so in order to do that, I'm going to use something called tensor networks. And this is the interactive part of
talk, so I just want to know, like, how many of you have heard about tensor networks before? Just raise your hands. It's like very few. How many have worked with them? Nobody. Okay, that's good. And we learned some new methods and new tricks, so that's fine. So in order to introduce them, I'm going to have to introduce first some graphical notation, where I'm gonna just replace vectors and matrices by nodes and edges. So tensors for me, and for the purpose of this talk, are just multi-dimensional arrays. So maybe that's more familiar if you're a computational scientist. You just have an empire array with more than one index. So you can have a vector, it has only one index, so I represent it as a node with one edge sticking out. So my matrix has two indices, so I get two open edges. I can have rank 3 tensors and 3 indices, so I can have 3 open edges. And the purpose of doing that is that I can visually represent matrix multiplications or vector matrix multiplications very easily just by connecting the open edges. So when I write this, actually what I mean is that I have this vector object here, I have a matrix object here, and I'm summing over this dimension of the matrix. So in this way, I can just write down graphically very more complicated contractions, and I don't have to write these sums over indices that you will get very dizzy very soon. So that's just the main point. So I have different arrays, and the tensor network tells me how I should contract it. Yes, please? Oh, the column. Yeah, so yeah, you have to be careful which one is which exactly. So if I say that this is the first index, then I sum over I. Yeah. But so this is graphically speaking. Maybe I could have better said that this is the second index. Yeah, it doesn't really matter. But it does matter for the result. Indeed, if you connect this one here or you connect that one on the bottom, you will get the result. But the point is that I can just graphically give these sort of big complicated tensor contractions. I can just represent them graphically, and then know like, oh, the answer here is going to be a matrix because I have 2 open edges sticking out. So how is this going to help me? So first of all, let's go back to the object of interest. I had this vector of probabilities, and the components of that vector were all possible configurations of the network that I'm studying. So all possible colorings of that network. So this vector has one dimension who has 2 to the n components, or d to the n components. So the first thing I can do is just to reshape that into a rank n tensor, which has n legs, where each leg has d components, where d is the physical states of the system, the nodes that you have in the system. So this really represents, the first component represents the susceptibleness of the first node, and the second component represents the effectiveness of the first node. So far I've done nothing. Like, this is just reshaping, no approximation. The point is that I'm going to approximate that object as a array of tensors that are contracted over an auxiliary internal dimension. So I'm going to represent each node gets its own tensor, and that still has the physical dimension, which represents the physical state of that node, but it also has some auxiliary direction, which is called the bond, which has a dimensionality called the bond dimension, that connects it to the rest of the network. And okay, so how is this going to help me? Well, this just counts a little bit the components. So on top I had d to the n components, where d is 2 really susceptible factors, but you could add more states. It quickly becomes intractable. You cannot store d to the n components in your computer for large networks. That's impossible. Here, I have n tensors. Oops. Each one of them, well, forget about the boundary ones. Each one of them in the middle has one physical index and two bond indices. So I have d times n times chi squared, where chi is the one-dimensional components. And so depending on what is chi squared, that could be a lot less than d to the n. So if chi, my bond dimension, scales polynomially with the system size, then I'm already doing better than the exact. So that's the idea, to get accurate representations in terms of these matrix product states, where the bond dimension is at best sort of polynomial in system size. So it should not be exponential. Of course. What am I interested in? Yeah. So I'm going to now take that. So what am I interested in? That comes in the next slide again. So I'm going to take that master equation of my process that's generated by Q, and I'm going to find the steady state. So I want to get them, and I'm going to suppose that I can approximate my probability vector as a matrix product state. And now I'm searching over matrix product state solutions to this guy equal to 0. So essentially, no, I could actually. I'm going to represent the state of a network with the matrix product state. So I'm going to compress. I have to order them, yes. So I have to order them, but that's a practical problem. You can. So what we found was that the ordering that works best is according to so the Fiedler factor of the graph. So you take the Fiedler factor and you minimize sort of the distance between different nodes, the correlation distance between different nodes. It affects, so the ordering affects indeed the bond dimensions that you have. The possible one. So I have to solve this. I have to solve this eigenvalue problem where the left-hand side of this equation is 0. So basically, solving for the leading eigenvector of that matrix Q. And in order to do that, I'm going to represent Q as a matrix product operator. So that's just like this matrix product state, a one-dimensional array of tensors, which now have two physical indices. The top one representing sort of the state where you are in, and the bottom one is the state where you are mapped to by this stochastic process. And that map from Q to a matrix product operator is something that you can do exactly. And the bond dimension of the MPO will then just grow maximally with the number of edges that you have in your network. So there you will not lose anything. And then what you can do is formulate the optimization problem as sort of optimizing each little tensor in the MPS one by one, so sequentially. So instead of optimizing the entire state all at once, I'm just optimizing one tensor by formulating a smaller eigenvalue problem, solving that, replacing that tensor with the leading eigenvector, and then moving to the next one, and then sweeping across the thing back and forth until the thing has converged to the optimal solution. And there are many tricks and things you can do. It's not something that we've thought of. This is coming from this condensed matter literature. There's a review paper here. You can also optimize. Actually, what works better is optimizing the two sides at once, and then you can actually dynamically adjust the bond dimension that goes between those two sides. But at the end of the day, if all goes well, you are left with a state that is the global kind of leading eigenvector of that transition, the Markov transition matrix Q. So this is still, this algorithm is called the density matrix renormalization group, so DMRG, but it still doesn't really tell you like what kind of bond dimensions should I choose, how large can they be, when do I get good accurate approximations, and when is it very efficient. So in that respect, it's good to talk a little bit about sort of how do you compress those bonds between the nodes. So here I have an example network. It's quite small, just a cartoon picture. Of course, it can be bigger. So indeed, the first thing you have to do is map these nodes to some specific border in MPS, to which I use the feature vector ordering, which minimizes square distance between these nodes. And then when you have that ordering and you've trained the MPS, you can actually think about each bond between two nodes as making a partition in the network. So if I, for instance, if I cut this bond here, I'm separating these 4 nodes and these 5 nodes into two groups, which is actually just in the network, basically not just containing the correlation between that node and that node, but actually containing the correlation between this whole half of the network and the other half of the network. So each bond makes a partitioning of the network into 2 parts. And then if I just take that bond, just take those 2 tensors that represent the bond, what I can do is perform a singular value decomposition. So I write that bond as a unitary matrix times a diagonal matrix of singular values times another unitary matrix. And what this does is that the unitary matrices are essentially just basis state transformations. So they are going to tell me what linear combinations of basis states on the left and basis states on the right of that cut are the most important to capture the correlations between the two halves of this network. And the singular values tell me indeed the largest singular values are the most important, and I can look at that spectrum and it's going to drop at some point, and I can say, well, if it's dropped below a certain threshold, I'm going to throw away those singular values. So I'm just disregarding some linear combinations of basis states. I'm saying these are not important to describe my state at this point, and I can just forget about them and still keep a very accurate representation of the larger state. So this is how you sort of trim the bond dimensions and make sure that they don't get too big. But actually, sort of philosophically, we can also think about this as, giving a measure of how compressible is your state, or actually how incompressible is your state. Because if I take this singular value spectrum and I compute this entropy, that's going to tell me something about the incompressibility of that bond. Because if only one singular value is there, then that's basically telling me that, well, the entropy will be 0 then, and that's basically going to tell me I can actually write these 2 nodes as a direct product, so they're statistically independent of each other. Whereas if the singular value spectrum is very flat, that's going to say then I get a large singular value entropy, and that's going to tell me I can not compress the state. So it's giving a measure also on how complex really is that state. And so if we now look at some toy example of a small network, so I have some graph, and I have set some parameters to these values. So lambda is the effective transmission rate in the system, and so as a function of lambda, I see the blue curve gives me the overall prevalence in the graph, so the density of affected nodes. It goes from 0 to some almost 1, and then there's this transition in the middle. Then the sort of normal signature of the transition can be looking at where there's the variance in the density peaks, the variance of affected node that peaks sort of on the onset of the transition. But if I look at the entanglement entropy, or the entropy of the singular value spectrum,
that peaks on the disordered side of the transition. So it tells me that the least compressible states in my Markov chain are actually on the disordered side of the phase transition, kind of in line with this intuition that the more complex states are at the edge of the chaotic machine. So and this is something that's this is just a finite size network, but it's something that's robust. If you do finite size scaling and you see where the peaks of these curves go, they don't go to the same thing. This one goes to the epidemic threshold, but this one always stays above it. Um, so in sort of the next couple slides, I want to compare like 4 points of lambda and find out the efficiency of these things. So one will be in the observing regime where there's almost no prevalence. One will be where the variance is maximum. One will be where the dynamic entropy or the single value entropy is maximum. And one will be over here in the endemic regime. So these are those 4 points. And then we look at how well is my MPS doing compared to the exact result. So that's why I'm generating small graphs, 16 nodes or so I can still compute the 2 to the n distribution using exact diagonalization. And I'm going to compare the error of the MPS, which is the blue curve, with the error that my mean field approximation makes and the error that my pairwise approximation, so the second order mean field, which is where you take the pairs into account as well. So if I'm an absorbing regime, actually mean field does very well, so why would you do this? But if we are in the region where you see the onset of the transition or where you see the maximal entanglement peaks, then the mean field is not so good, and the MPS is sort of tunably better. So it starts bad, and then when you have sufficiently amounts of singular values that you take into account, it starts getting much better. And the same at this maximum entropy. It's really having a problem to get a good, accurate description if you don't have sufficiently large bond dimension. But if the bond dimension starts increasing, then you start to do much better than the mean field in the second order mean field. And that's sort of robust for different types of networks, but they're all small networks. Anyway, the point is that in that regime where the entanglement is maximal, so the state is sort of the most incompressible, you really have to make sure that you take sufficiently large bond dimension. These are Sogas, but the picture is the same. It's very similar. And this is just showing for all these different networks how does the entropy of singular values converge, and that's you see that if the bond dimension is too large, then it's kind of all over the place, but at some point you have enough room in your auxiliary bond directions to capture all these correlations in the singular value. The singular value entropy doesn't increase anymore, so you know you have an accurate description. So this is all kind of from small networks to do something larger, but still small for complex systems people. This is something that you would not think about doing with exact methods because we have 55 nodes, so 2 to the 55 is really infeasible. But with the MPS you can get a good description, and it's like a toy network of the Dutch train railway system, where you see that still sort of the correlations are very important because it's a geometrically organized network. You see quite some mutual information around the threshold. But if we see here, the solid lines are what the MPS, the dense network, gives us for individual node preferences, and the dotted lines are from the mean field. And you see that there's quite some disagreement in when the transition takes place. And then we'll have to see like what's actually better, what's the ground truth. Well, if we compare this with Monte Carlo, then you really see kind of like the Monte Carlo error and the MPS error is of the same order of magnitude. I could have maybe gotten more Monte Carlo, better Monte Carlo
longer, but and patience in any case is doing much better than mean field or second order mean field in that case. But also the point is that if you have this sort of representation of the exact distribution, you can also ask it questions that you can't ask from mean field, or that are difficult to ask with mean field or with Monte Carlo. So it's kind of complementary in that sense as well. You can look, for instance, at probabilities of very rare events, and even that is kind of simple to adapt the methods just presented to really study also the large deviation theory of these kind of systems. You just have to optimize for the leading eigenvector of the tilted generator, and 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 then you can get insight into the statistics of rare events. Also, if you have that MPS state, you can also ask questions like, what is the probability of having exactly n infected states, or n or more infected states? And these things, depending on lambda, those probabilities get really small. So those would be very hard to see with Monte Carlo representation. Okay, so my take-home message: these tensor network methods allow for tunable improvement of mean field approximations and give insight into compressibility and complexity of these full distributions. Then I have some conclusion and outlook slides that has lots of text on it. I'll just leave it here, and then I'll just take the time that I have left to answer your questions. So thank you very much. Yeah, that's a good point. That's a good point. Like this, so this is relating indeed to like what's the inverse problem. This is everything that I've presented here is very much forward, right? You have the model, you have some network, you have some interactions, and then you look at the distributions that come out of that. It's very interesting to think about how we can adapt these methods to indeed do this coarse graining in a smart way. Because even if you use this, then yeah, it's to get to larger and larger networks. It's quite difficult still and quite hard. So you want to get a sort of integrated coarse graining procedure, and there are also other type of tensor network ansatses that perform that do a sort of renormalization group on the degrees of freedom that you have at the bottom of that form. And so I'm thinking along those lines, but really like going from the data and trying to then infer what is the model or what is the complexity or where you are in that sort of graph of compressibility. Yeah, I don't think we're quite there yet. Yeah, so it's
I mean, this is a good question and a key question, I think. And the thing is, the answer is it depends. Because it really depends on also what is the complexity of the network that you're studying. How, for instance, I am trying to squeeze the network into a single line, so I have sort of, if that network is mappable or easily mappable to a single line, it's going to be easier. Uh, I can even take the 1D SIS model on a 1D array, and it will get much easier if I'm in the. I mean, I could then even use translational invariance to make an ansatz which works in a thermodynamic limit, let's say. So if you have these kind of regularities, it becomes easier. If there are now also in the Dutch network community some sort of hybrid algorithms that use, for instance, belief propagation in combination with tensor networks, and I believe that will be able to get you will be able to get to larger networks. Um, and it depends very much on sort of the complexity of the dynamics taking place as well, because even with my sort of moderately sized or moderately small networks, right? If I'm in the absorbing regime, I, it it will be very fast and very quick. I'll get very low from one dimensions. But if I'm close to that maximal singular value, I will need to get very large combinations. So it depends not only on the network structure, also on where are you compared to the phase transition, how close are you to the transition that's going to grow. In the endemic regime, in the absorbing regime, there might be some hope that if you grow it, it will just go to a constant or proportional to n. But if you're close to the threshold, the bond dimensions are also going to grow um, with sort of the closeness to the threshold. So that's a thing to consider.
I think in the interest of time, we should leave it like this. We're almost one full talk late, so it's my fault. But yeah, let's thank again. And let's welcome the next speaker of today, Christian Rodriguez Camargo. Christian is going to talk about consensus dynamics and optimization in higher order networks.
Hi everyone, thank you for having me here. It's really nice to be here talking about complexity near to close to La Alhambra. So it's my first seminar, my first Granada seminar, and I want to show you like the line of thinking about how to achieve a generalized consensus optimization over higher order networks, and ask you a lot of questions about that. So let's start with the consensus dynamics, defining what is consensus dynamics. So it's in a sense to push the agents in a network to reach an agreement about an scalar state. In particular, you commence with the start with you push the agents to meet a specific common location. In the consensus dynamics, you are specifying the state of an agent, and you only have that agent only have information about the neighborhood. There are some communication about the neighborhoods. The information is running just locally, but the final result is a macroscopic behavior of this kind of things. So in terms of control, you can assign to the dynamics of the state a single integrator dynamics and in an easy way to obtain an agreement between the agents, you could drive each agent towards the center of a neighborhood set as this. So this is known as the consensus equation. And if we establish these neighborhoods given by a graph, going to the fundamentals graph theory, you could rewrite this equation in terms of the degree of the nodes of that node and in terms of the adjacency matrix. So you can rewrite all the dynamics as the Laplacian of the matrix multiplied by the vector state. So this is the complete consensus equation. So keep in mind that we can modify this equation, this consensus equation, adding a font term to obtain dynamics of leader follower, geometric formation, game theory, distributed estimation, and collaborative robotic sensors. But the important thing here is that your consensus dynamics is strongly driven by the Laplacian of the graph. On the other hand, talking about diffusion dynamics, you have that the operator driving the diffusion dynamics is the Laplacian in the continuum Euclidean space-time. Yes, but if you go to a discrete space-time, and in particular, if your space-time is described by a graph, you can show that this Laplacian operator will be the Laplacian matrix of the graph. This paper is so beautiful because they are departing from first principles to show that effectively the dynamics of the state variables on a graph will be driven, the diffusion dynamics will be driven by the Laplacian matrix of the graph. And even from that, you can show that you can construct all calculus theory in discrete space-time, and in particular in a graph space-time, and all the differential operators are given in terms of the Laplacian matrices and boundary operators. And you can explain that in Schrodinger equations. This paper as well is so beautiful because if you see the Schrodinger equation is a diffusion equation with imaginary time, no? And so you can construct the Schrodinger equation in a graph space-time, and you can show that effectively the Laplacian of the Schrodinger equation in the continuum will be the matrix Laplacian of the graph. So what is the message of this? That you can relate the diffusion consensus dynamics are so related with the diffusion dynamics. I could say that even we can have a kind of equivalence situation between diffusion dynamics and consensus dynamics. So you can take all that you know about diffusion dynamics and compare and take the Laplacian operator, go to the Laplacian matrix, and see what is happening with the consensus dynamics on graphs. So in principle, in diffusion dynamics, you can do everything with the zeta function formalisms. So we explore that in the direction. We generalize it, the zeta functions to obtain what is happening, what are the thermodynamics of random networks, in particular with the spin glasses. But more interesting, we construct a set of new spectral set of functions based on that to construct robustness. We applied that to growing algorithms, and we saw that if we use disordered set of functions to grow networks, are kind of different, but varying the disorder of this kind of set of functions, we can construct more communities, or we can grow a network in a different way. But it is just the starting point of that, because the important question to discuss here is the distributed consensus based optimization. So in two tasks previous of this, we see that the classical optimization problem is to minimize a function to find that minimizer, and the way to obtain that minimizer is with the gradient law. No? So in the distributed optimization problem, each agent has to minimize the function, but the function is just known by the agent. The agent only knows information locally, and all the system, all the network has to minimize a global function, which is the summatory of these functions of the multi-agent network. So it is widely used in smart grids, in collaborative robotics, and in sensor networks when we have just a knowledge about the neighborhoods, but all the grids, all the network has to achieve a minimum in the in the in a function. It could be a cost function, an energy function, what you want. So to obtain that, we have to obtain the minimizer, we have two kinds of constraints. One is the Laplacian constraint, and the other one is the incidence constraint. We will find these kind of constraints in the topological case when we have the Laplacian of the simplicial complexes or the Dirac operator. Okay, so you construct your Lagrangian function in terms of your, for example, if we choose the Laplacian constraint, the Lagrangian function will have the Laplacian and the corresponding Lagrangian multiplier. You do the dynamics of that Lagrangian function and you obtain this. So the evolution of this state will be the minimizer of the function to be optimized. And we have that effectively we are arriving to a consensus equation with a font term. So we say, okay, effectively, to obtain distributed consensus optimization, we have to find a set of different Laplacian operators or diffusion operators and see what is happening in other kinds of systems. So we start with the hunting of these different diffusion operators in discrete spacetimes. The first victim was the diffusion operator on multiplex networks, and we take that supra-Laplacian defined in this paper, and we obtain it a consensus algorithm over multiplex networks. So we generalize it from single network to multiplex networks. But what is a multiplex network? A multiplex network is a multi-layer network with one constraint that each layer has to have the same number of nodes in each layer. And there is a correspondence one between the nodes of a different layer. So we apply the same thinking. We say, okay, we have an operator which is driving the diffusion in this kind of systems. Use that operator to construct an algorithm of consensus, of optimized consensus, and see what is happening in that. And we obtaining that effectively, or gradient descent algorithm for this is working perfectly well. The different agents of the multiplex network are reaching the consensus, but it's a special consensus. No, is they are reaching a value which is minimizing the function to be optimized. We apply this to power split networks. In this case, we can add some constraints. Yes, and we obtain an interesting behavior of the consensus time, because if you see, I don't know if if that could be named as a phase transition or discontinuous, but the you see the expected behavior as you are increasing your diffusion constant, obviously, is more difficult to reach the consensus. But it is not a continuous. You have special values of your diffusion constant in which it is reaching a phase in which it's difficult to reach the consensus, and if you increase that or that parameter, you are requiring a kind of connectivity. No? So that finding was interesting because you cannot simply arbitrarily vary the diffusion constant in these kind of systems. Okay, but what is the problem with the multiplexes? You have to have the same number of the nodes in each layer, so it is not so general. So we went to this paper to the mathematical formulation of multi-layer networks. They established here a tensor formalin to generalize all the multi-layer networks, and we extract for them the Laplace, the tensor Laplacian diffusion operator for this kind of systems, generalized subsystems, and we obtained these results. And it was accepted after 1 year of back and forth with the referees because the principal discussion was why are we using tensors? So this is why the you use tensors, you could construct in a better way, and you are not losing information about the complexity of a multi-layer network. So, for example, you could have a lot of different layers. In each layer, have different topologies, different numbers of nodes, different kind of connection between of nodes, and you can arbitrarily assign a connection between each layer. And all that information is condensed here in this object. This object is telling you how is it interacting the node I with the node J in the layer H of the and in the layer K. Okay, so you have a totally general parameter here to generalize all these interactions. Okay, so we construct our tensor Lagrangian function to develop our algorithm of distributed consensus optimization in these kind of systems, and we obtain these dynamics for the tensor state of each node. So this notation is telling that this y state corresponds to the node beta of the layer mu. So you are having the complete information, no, regarding and connecting with the tensor Laplacian tensor with the tensor Laplacian of the multilayer network. So as well, we use a toy model where we an arbitrary different layers with different topologies, with different nodes. In each layer, we have as well different interlayer diffusion constants and intralayer diffusion constants. We can manipulate everything here, and effectively all the agents of this multi-layer system are reaching a consensus, and I repeat, I insist, this consensus is not any value. This consensus is a value which is optimizing a function of the multi-layer system. And as well, we obtained a similar behavior here of showing the multiplexes case, in which we have a discontinuity in the dynamics of the consensus time. I don't know if we could name that as a phase transition, but we could name the diffusion constants as a parameter orders in this kind of situations. So not necessarily to augment the diffusion constant, we lead you to a reduction of the consensus time. Okay, the same varying, for example, in different times, nor all the permutation of the consensus of the diffusion constants will give you that phase transition, but we can obtain some certain of discontinuities in the dynamics of the consensus time uh, for different arrays of diffusion constants. And even when we induce perturbations of the nodes, we are obtaining that our algorithm is robust in front of damages, in front of different kind of problems in each node, in terms of error propagations about all the layers. It doesn't matter. Effectively, our algorithm is pushing up the agents to reach the consensus, to reach the optimal value, which is minimizing a function. What kind of function? It could be energy for smart grids, for example. It could be the cost dispatch energy, the cost price, as you want. Okay, but well, one of the principal messages of this seminar is we have to move beyond the firmware's interaction, no? Because here we have a generalized context, but we have firmware's interaction. No? So we have to move simplified complexes and obtain a consensus algorithm, distribute a consensus algorithm to that kind of systems. So the we have that for single layers systems or a variable state is it could be a vector. After with the multi-layer we have tensors, and the evolution of tensors is an spinor. No? So the spinor is telling you how can be the dynamics of the states of the nodes, of the edge, triangles, or even more generalized um, structures. So, as well, the dynamics of this spinor could be obtained with diffusion processes with the large Laplacian. We see the first slide in the talk of Professor Ana. But we can put to evolve to explore the temporal behavior of this spinor with a Dirac operator. And remember that the Dirac equation is the relativistic version of the Schrodinger equation. So putting all together all the pieces of this puzzle, we say, okay, we can obtain a generalized algorithm of optimized of distributed optimization over these differential complexes with two ways. In one way, with the Hodge Laplacian, which is related with the with the simplicial complexes, and the other one with the Dirac equation, because the Dirac equation is telling you as well how is the diffusion over this kind of discrete space-times. Here we have an excellent review of this kind of results. We can systematically evaluate what is happening and where is the relation between the diffusion with the Hodge Laplacians and the diffusion or the time evolution with the Dirac operator. So the first part, we can construct an algorithm with these objects, which are defined in terms of the boundary operators. But the other option is to use the Dirac operator. So the Dirac operator and the Laplacian operator, they are related in this way. So let's study what could be the difference between the consensus of these two. So the objective here, we have a function of each of the state of each object here. That could be an edge, could be a triangle, could be a node, and we have two kind of restriction. We have a restriction given by the Dirac operator or given by the simplicial Laplacian. We are running in this moment simulation just with the Dirac operator, so we are obtaining our version of that Dirac dynamics with this gradient flow, which is achieving, with this pushing all the agents or all these kind of structures to reach a consensus, but this consensus is an optimal value which is minimizing this function, which is a function of a state. It could be energy, it could be as you want. Okay, but I have a lot of questions for you about this because okay, my advisor always says me, Christian, remember that you are in a physics department, the mathematics department. So please, okay, you are demonstrating that effectively these operators are so well behaved. We have uh, we have the properties we just established, and with that properties we are showing with different Rose theorems that we can achieve the topological consensus with this kind of dynamics. But for what? So I give you here a set of questions to think about. You are watching the marvelous sunset in Alhambra. So the first one is, what does it mean to have topological optimal consensus in real-world networks? For example, you see that the most fundamental things in physics are obtained with a variable principle and with a minimation principle, in particular with one quantity, which is the action. With the minimation of the action, you can obtain the Schrödinger equation, the Euler equations, the Einstein field equations, and even when you construct all your theory with the in terms of action, in terms of the Feynman integrals, you can extend all your formalisms from gravity, for example, to thermodynamics, to mechanical statistics. So I think that we can use that kind of things and explore what is happening in the nature, and if the nature is tending to reach that optimal value of, I don't know what, of action, of energy, another kind of physical quantity. And in that kind of interesting networks that you see in this seminar, the great message is let's do what is happening with these networks, but transcending, going beyond the pairwise interaction. In this sense, so which is better between the Laplacian used to explore the nature of the consensus, to explore the nature of the distributed optimization in real-world networks, in the nature of networks, which which operator is showing us more information, or the Laplacian, or the Dirac operator, or even we have to construct another one, another more, but following the same pathway of the quantum physics. With the Dirac spinor, you have all the generalization. It is it is reached a general structure to explore the particles, and in this case to explore the simplicial complexes. Do the systems prepare any of them? Do we have topological optimal consensus in nature? And what can we learn from these processes in the brain? And so the invitation is, if you have any systems to apply this kind of optimal distributed optimization, and you are feeling that the nature is looking for an optimal value of any quantity regarding that network, please just contact me and we can talk about that. That's it.
Thank you. Questions? Yes, I have a question. You showed this, I don't know if this is phase transitions with several slides. For example, when you were talking about multiplex networks, you showed that this time causes, yeah, like it's minimum, no? With the diffusion. Do you understand why and what is that value related to? Is it related to anything specific of the network? Does it mean something specific?
We are asking for that. Yeah, yeah, yeah. I don't know if it's a particular value, it's a particular numerical, but I think that is totally related with the topological because when you are exploring just diffusion, in diffusion, you are obtaining as well that kind of discontinuity dynamics just with the eigenvalues of the Laplacian matrices. So maybe it's in that direction. Thank you.
Any questions? So maybe we can move on to not eat too much of the lunchtime. That's great. Let's thank Christian again. So we can welcome the final speaker of this morning session, Adrián Aguirre Tamaral. He will talk about living systems and in particular phase transition and adhesion in tissue architecture.
First, I would like to thank the organizer for giving me the opportunity to talk about biophysics, in particular in the context of tissue architecture. Just for the beginning, let me frame a little bit the topic in developmental biology, which is the area in biology that tries to explain what you can build an organism. Coming from different levels of organization, how these levels interact in order to create a higher order, like for example, from molecules, how you can explain the different dynamics of the cell, from cells to the tissues, the organs, and in particular, my research is between these two levels of organization, trying to explain the biophysical properties of the tissue, understanding the relation between the cells. When you build all organisms, actually there is a huge number of events. The cells divide, they organize, they have to change the state in order to create the proper state of the tissues, and all this is coordinated in space and time. The classical view of this developmental process is that a molecular approach. That means that there are certain molecules, or usually morphogens, that has a particular information that are transmitted spatially to other cells, and this organization at the end arrives in the final stage of the limb or different organs or the tissue architecture. Probably you hear about this idea with gradients or reaction diffusion systems, also called Turing systems because they were described by Turing like around 50 years ago. And the idea is that you have different molecules, this can create a spatial pattern. If the molecules interact, you can create a more complex pattern, and this pattern is what the cells are reading in order to create the different properties of the tissue. But I will propose you a question, is like, if you look just into the molecular signaling, you can explain the process of the construction of the tissue. Because at the end, what you have is a lot of physical forces and a lot of spatial constraints at the same time. So just looking into the molecular signaling, maybe you are missing important information to understand the process. I'm going to give you a sample, for example, here in the zebrafish development, the cells start to divide, and there is one particular moment that the cells have to bend in order to create the different layers of the animal. This moment is actually starting the thinking, but actually at the same time there is a correlation in the space and time with a lot of physical things. There is like reflection, involution, there is a lot of forces that you cannot actually explain just looking the world. Actually, if you look at the interaction of the cells, there are cells that immigrate, they invaginate, they extrude from the tissue. So you need to know actually this kind of physical constraints. In particular, if we look this closer, what we see is that we have the development of the zebra. This part is the cells that are going to develop the full animal. This is just food, this is yolk. And when you have this in this particular model, the dome state, they start to run in order to create this state, which is necessary to create the organization of the tissues in the animal. And actually, if you look closer, the physical properties of this state, what you see, for example, in the viscosity, you have a high viscosity here that suddenly drops here and then is trying to recover here. This puts the idea in the field that here you have a kind of a transition in the properties of the tissues. And actually, the idea to model this particular behavior is to phase transition. So if you are coming from a solid like high viscosity state and you have to change the state, easy way to do it is just go through a phase transition that allows you to go through a liquid-like state where you have a minimal cost to reorganize the cells. So coming from here to here is easier and energetically efficient if you go through a phase transition that changes the properties of the tissue. Okay, so this is like motivation, but how we can model this phase transition? What is the order parameter? What is behind this transition process? So if we look at the tissue level, what we see is that you have different cell-cell contact. So there is not the same number of contacts when you are in the viscosity, the high viscosity, or when you are in the low viscosity. And actually, if you track the evolution of the number of contacts over the time, you see how the number of contacts drops and then it starts to increase. Just in the sac regions where you have a solid-like or liquid-like structure. If you measure the viscosity with the probability of contact in the lattice of the cells, actually what you see is that this particular moment correlates with the Maxwellian rigidity of a lattice-like structure. That means that actually what you are seeing here, you can consider the number of contacts like an order that is given you the information of the structure of the properties, the physical properties of the tissue. This actually allows us to create a really nice comparison to model the process because you have geometry where the cells pack, but actually you can extrapolate the information from that geometry in a topological view and try to understand the physical properties of this configuration looking at the topology of the network behind. Just to give you a sample, this is a particular zebrafish tissue, and we have a different cells marked here in gray, and then we have fluid between cells. This allows us actually to create a map of a network of how is the distribution of contact between the cells. And then we can use this network trying to study the physical properties of the material, the biological tissue. The idea behind this actually is that if you look at this network and you go to a particular material, if you move one of the nodes and there is no reaction against this movement, you can say that you are in a kind of a floppy motif. So that's the equivalent here is that if you have a floppy motif, you can deform the tissue without affecting the energetical force. But actually, just creating a new more link in this motif, you create a rigid structure that when you try to move against one of the nodes, this is reactive. So in this particular configurations, you have an energetical cost and the cells cannot move that easy or at least in a minimal energetic way. If you study this, actually the networks, you can see actually that looking the vegan cluster, which is the cluster of all the cells that are rigid, you can see that actually depend of the contact between the cells, you have a phase transition that actually correlates with this floppy and rigid line model. If you do computational experiments in those regions of the network, you try to perturb a little bit the network, you see that the mechanical properties and the material properties of the system can be explained through this particular correlation of the contacts between the cells. If we go to the experiment, we can actually track temporal evolution of the cells. We can try to take those cells and create the network of contacts, and then perform the algorithmic analysis trying to see what are the different clusters in those cells. And what you see actually is that at the beginning all the structure is rigid, then you have this drop, you lose the rigidity of the system, and then you try to recover the system, which is exactly what we observe in the physical properties of the material in the so we have this initial solid-like structure that is dropped into a liquid-like, is reorganized in the cell, and then is being back to be a solid-like. If we compare this with the experiments, we have a really good agreement in this transition of the properties and in the relation of the viscosity of this macro property of the tissue with a different cluster in the network. This is actually quite important because what you're saying is that the biology is following a particular trajectory in this space, that moving just the connectivity with the cell, you can change with a minimal energetic cost the microscopic properties of the tissue. But what is behind this process? So now we see that looking at the number of contacts, we can try to explain the properties of the tissue. But what is driving the change in the number of contacts, right? Typically, in the last, let's say, 5-6 years, more or less, people start to understand this as a jamming transition. You have a different number of cells, and depending on the density of the tissue, there is going to be a moment that you cross through this particular threshold where the structure becomes rigid. So, in this sense, what you are saying is like because of jamming, because you have increasing the cell density, you can control the different properties of the tissue. And actually, if you go to the experiments and you try to measure this, actually there is a really good agreement between the lattice, the rigid cluster, and the viscosity of the tissue. So those properties, macro properties like viscosity, are correlated with the rigidity of the network. And you can see actually in the temporal evolution that when you drop and you do the ligand component cluster, you are crossing actually the threshold of connectivity and the threshold in the cell density. So this is quite promising, and a lot of people say, okay, we already explained the process, but collaborating with some experimental people in the MBL, the Heidelberg, we saw that actually there are some particular conditions, experimental conditions, that do not satisfy the jamming transition alone. So for example, in this case, in this plant, what we have is a tissue below the critical density, which density is really critical, viscosity. But here we have this mutant, co-mutant, that you are below, so you are higher, has a high density, but actually you have a really low viscosity. So there is something missing here in order to explain the properties of the tissue. What we propose actually is that what is missing is just cell adhesion. It's not just that the cells are in contact between them, but also how strong is this bond. We can actually model this quite easily just going through a geometry equation where looking the geometry, you can create an observable that we call alpha, There is a relation of the surface space in different cells, and you can measure this quite easily through the geometry of the angle between the cells. Actually, this is quite nice because in biology, usually it's quite difficult to obtain an observable that you can measure experimentally in order to compare with the physical. In this case, with this relation, we have quite nice and easy observable just looking the angle between cells. And this is going to tell us what is the self-extension, the self-adhesion between cells. Higher alpha means not adhesion, a sphere, and lower alpha means that you have a stronger base. At the end, what you're looking here is just the force balance in the surface of the cells, and looking this, the surface extension, we can obtain that alpha is going to be proportional to the angle. It's going to be the percent of the angle between the cells. If we try to link this with what we know before of the networks, we can try to see what is equivalent with the motif. So for example, if we have this configuration of the cells, and we have this particular angle, we are in a floppy mode. But there is going to be a moment that if you increase adhesion, you reduce alpha, there is going to be a moment that you are going to create a new contact between cells. Then you are going to create a rigid motif of the network just changing the cell adhesion. If you calculate this geometrically, you think predicted critical alpha around 0.86. So having this, we were trying to say, okay, this is something that is happening in the reality, in the biological tissues. So what we did is just go to the experiment and measure this angle with this, and see if in reality there is this change when the properties of the tissue is changing. And actually, you can observe here that indeed a solid-like structure with low alpha cross the particular critical alpha exactly in the moment that it has to fluidize. The idea here is that we have the same configuration of this silent cell, but without changing the density, just changing the adhesion, what we are going to do is just create a rigid motion. We did these simulations with surface Bohlberg and computationally, and we predict that there is going to be a phase transition actually based in this parameter alpha, which is the parameter that causes the cell adhesion. So you can measure the rigidity, the gigant rigid cluster, just as changing the cell adhesion between cells. If you go to the experiments, then you see that this particular transition is in agreement with the experimental. And actually, you can see also this relation with the connectivity and the surface tension. So moving in this diagonal, you have the change between rigid-like, solid-like tissues and liquid-like tissues. So what we was observing before actually, it was this diagram. If you look, there are most of the experiments in cell fraction, because you are just in these two regimes, same cell fraction is same high cell fraction is same low alpha. Same high alpha is same low cell fraction. So it looks like it's working quite well. But actually, what happens if we have tissues in these three? That is exactly what happened with this mutant that I said before, and with this explant, where you remove this particular part of the tissue and you culture the. So those cases we cannot explain by cell fraction, but you can explain looking the cell adhesion between them. And actually, if you look this cell tension, surface tension, cell adhesion, again, it's the same, is a better indicator for the macroscopic properties of the tissues, like, for example, the viscosity. looking alpha, you can actually see a better correlation than just looking um, cell fraction. Well, this is just more measure about this. But what is important here is that we can change this. We can just, instead of going in this diagonal, we can just go to other part of this diagonal. And actually, because this conference is also about new methods and tools, I want to present these experimental tools that Nicoleta Petido Group and Miguel in Heidelberg was performing and developed, which is really nice experimental tools because allow us to test physical ideas, physical questions that usually is not easy to test experimental biology. So what they do is they design some drug experiments and some optogenetic tools where you can, using light, change the genetic switch off and switch on of the different proteins to change the vision of the cells. So we have structures that are floppy and we can convert it to rigid using this structure, but we can also change the cell adhesion, converting, for example, something that is rigid in something that is floppy. Also, we can combine those tools, experimental tools, so we can go actually in multi-layer density and cell adhesion. So actually we can start here and we can move from here to this regime, from here to this regime. So we are able to explore experimentally all the configurations that we are proposing in the model. This actually, what we usually see is this couplet alpha T in this diagonal, but if those parameters are coupled, you can move to other part of the diagonal. And this is working project, but something really interesting here is that we are changing experimentally just the physical properties, the physical constraints of the tissue. But what we see with electron microscopy is that we have some signals that the destiny of the tissue is changing. That means that coming from a particular group of cells, just changing the physical constraints, if we induce fluidification of fluidization, what we can change is the final destiny of the tissue, creating like lumens, structures, creating different pathological or wanted conditions. So here we are changing actually the classical molecular approach and say that if you have different molecules, this is what at the end is going to drive the final shape and the destiny of the tissue. But here what we are doing is changing the physical constraints and we are moving from different trajectories to creating different types of tissue. And what we are doing now is trying to see that actually we have molecular markers that identify those change physical changes are indeed changing the molecular identity of the tissue. All this work was possible thanks to a really nice collaboration between the Bernardo Mostra group in the University of Graz and Nicoleta Petido group in the NBR. They are doing amazing work. Experiments. Really, it's really nice to have this possibility to compare the simulation and the physical theory behind with experiments to have this feedback. If you want to read a little bit more about this, we already have this event. Hopefully it's going to be published soon. We are in the second edition in statistics, fingers crossed. But if you have more questions about epigenetic, the epigenetic tool, or how we derive the physical equations of the Hamiltonian that is driving more balance in the process, you can go to the perfect. So if you have questions, or also you can email me if you want more particular. Thank you.
Okay, thank you very much for the talk. I was wondering about the. Okay, so at the beginning you show a kind of rigidity transition based on network, which I guess all the links are equal in some sense.
Yes.
And then later what you do is you take into account addition between cells. And I'm wondering what kind of effect it has on the. I guess this affects the kind of strength of each edge of your effective network in some sense. I guess you are doing other kind of simulations. You are not using the network anymore, or are you using a network with weighted edges or something like that? Or is that
Actually, it's a really nice question. It's not exactly what we are doing, but yes, we are aware about this. What we have is that actually here, if you look the cell addition and the properties of the tissue, one of the things that you are, um, one of the things that is happening here is that when you are crossing this, you are also closing the three cell junction between the cells. That means that you are creating triangles in your network. So you can actually measure, we were doing some analysis about the three-cell junction of the triangles when you close the triangles. And what we see is that actually, if this is rigid, but it's not a concatenation of triangles, then you are not taking into account the cell addition, just looking the cell density. But if you look the concatenation of the triangle, then you can, without putting a strength in the link, you can actually see the properties of the tissue just looking the concatenation. This is actually something that you can do instead of looking the gigant cluster, rigid cluster, is just looking the M form, which is actually giving you this idea that what you are measuring is the cluster, the biggest cluster that is formed by triangles.
Okay, so if there's no more questions, let's just thank again all the speakers from this morning session. And I guess we be back here at 4.